Antariksh Karishma. Hey, nice. Okay, so let's then get started. Look, there's these four characters, and this character has a little teddy bear friend. Look right there. Teddy bear. Okay. Pretty soon that'll be you guys for the midterm. OMG, the midterm is coming up. Oh my God. We'll definitely talk about the midterm. And I'll have most certainly a sample for you so you can see what kind of questions I ask. The questions are not difficult. The questions are not subjective. In other words, there's not too many different ways to answer it. But the questions are open ended. They could be open ended. It means you can answer anything reasonable. There's not just one expected answer. It's a lot like even your homework problems, right? For SQL, there's more than one way to solve it. So I don't look for the official way. So as long as you're on the right ballpark, you should be okay. Anyway, you will actually see that when I show you the sample. This is all about business intelligence. So let's actually do that a little bit in the second half. Okay, so I have nothing else to already like add to what we said. I'm gonna start the discussion, start the lecture that is. It's like this, right? So we started looking at data. Data is a uniquely human activity, data gathering, data analysis, data usage. So that is where it all started. And then we quickly said one of the best ways to enter data is through tables. And so that is the notion of relations, because a table is called a relation. And then you can have relationships between tables. So that is the ER diagram. Then you could extend that, and then you could take tables clean. And this was all your homework. So you guys all did finally pretty well. There were lots and lots and lots of questions, of course, because it was not a trivial homework. It was not a difficult homework either, but it definitely made you think. It made you ask, what kind of data do you need? It made you question your homework when designed, if you should modify it, and so on, right? In other words, it's a good learning experience. Yeah, thank you. I'm glad you thought it was fun. It's a little bit, I'm not going to say frustrating. It's a little scary initially to start, like, wow, where do we even start? But once you get going, you put some tables and some data, it shows you the way. And then it tells you what more do you need to do? What more do you need to do? That's a good question, Krishan. Would we get feedback? I'll try and find out, okay? I'm not sure just because the midterm is basically next Friday. I'll see what we can do. If we can, we'll try and get you some feedback. Even if not the official score, but maybe some kind of feedback. Okay. And then, so that is all the SQL world. And then we said, yeah, next week, a part of next week is the review, not all of it. I do have like so much, it's a packed schedule, as you can tell, right? So yeah, we can spend some time reviewing, but not all of it, which is kind of what I did for CS 571 just yesterday. The exam is actually tomorrow. And so they had a little review. So we'll see what we can do. All right. So transaction management is when all this was happening, in tables with data with SQL, but then not just one person, but thousands, if not millions of people. And so we had to, get it right. That is the notion of transaction management. And the short of that is locks work wonders, timestamps, they work wonders. So one way or the other, we can do transaction management. It's not a big deal. And then likewise, this notion of distribution. So then we said, what happens when you not only do transaction management between multiple people, but even for just one person, their transaction happens to involve multiple servers geographically distributed. So then if one fails, then your transaction would fail. It has nothing to do with the other people. The other people are still there, but now you have your own problem because you're distributed. So we can solve that too, to a good extent. That's the two-phase commit idea. So we went through all of that. And then last time we started doing this, I said databases are so much fun when you actually hook them up to the internet. And then anyone with a smartphone is able to query all of that. So that was the notion of connectivity. And then we started doing performance tuning. This is when we said at the server level, the server can gather statistics and then try to fetch your data as efficiently as possible. So we're going to continue that today. Like, what can the client do? In other words, what SQL can you write to help that? And also, how does the whole overall fetching of data execution work? Like, how does the SQL cache, data cache, like all of that work? So today we'll finish that. That's why it's continued. And then we can also start on this brand new topic of business intelligence. As it says here, all the content above this line are included. That means what I say today would be in next week's midterm, okay? But this will not be on the midterm because that is literally Wednesday and Friday. So, there's only 2 days. Plus, we draw a nice line conceptually, and this is the start of a new world with like new kinds of data and then new ways to store data. So we'll keep all that for the final, okay? The final might mostly only be about the second half. In other words, it is what it's called not comprehensive, just the second half. But obviously, it's not like you can throw away the first half because things still go back to all this, okay? So you cannot expect 0 questions from the first half, but the focus will not be on the first half. It'll be on the second half. Okay. So all that said, we're going to do indexing, okay? So one of the main things I didn't tell you was how indexes work. And indexes are wonderful. They really, really speed things up. So how does the whole SQL query engine work together with indices? In other words, how does it use any index that you created? And then how come that makes the queries go fast? So we're going to look at some neat things. It's roughly like with the first hour, okay, till about 6:15. Some of this is repetitive because we already did it. We call this whole idea tuning, just like tuning your car or tuning, some kind of oscillator. You want it to have maximum resonance. And so how do you tune it to get optimum performance? So the tuning is ultimately in 2 very different parts. One of them is you can tune the backend database, and then you can tune the front end queries. I already told you this. We'll spend some time on this picture a little more today, which is to tell you, so once you issue a query, you're searching for some catalog on your phone, and then how does it come all the way back to the pages refreshing and it shows you what you want? So how does that loop happen? And some of this we already mentioned. Today we'll focus more on like this part, and maybe on this part, like 1, 2, 3. Mostly what happens is this initial process will validate your query with access rights, pass it on to this one. So then they work back and forth. If there's a syntax error, then it goes right back. Even in your Oracle homework, you probably noticed if you left out semicolons or parentheses, your query is not going to even run. That's all because of the listener. And then if things pass, then you get access rights, Then afterwards, these things take over. So this is where they've already done their work. It means your query is now running. So it's really all about this part. This is the one that can potentially make your query run faster. That's why it's called the optimizer. And so the job of the optimizer is to then, in the most optimal fashion, use this as least as possible. You want to not tie this up with your query. Get the actual data that lives on these tables and store the data here, and then do all the execution here as well. So the processor here is running through all your data, doing your actual SQL query, what. And then it's going to return the results. So the return of the result is called result set. We've seen this in the past, XML result set, Python result set, result set. But interestingly, this part is actually called fetching, okay? It's called fetching. Fetching is to go from here to here. You would think that fetching means they're fetching you the result, but that's not fetching. Fetching is fetching from the actual tables to the data cache. Okay, so we'll spend some time on that. Meaning you will understand like what the different pieces are there. And then, yeah, these are all things we can skip. So your data is not stored in, well, your data is stored in binary files called data files. Obviously, tables are data files. But when you extend them, when you run out of space, you don't extend just 1 megabyte and keep extending it over and over every few seconds. You might extend in a large chunk, so you don't have to keep extending many times. But you don't want to extend many terabytes at a time either. That's too wasteful. So there's always some happy medium that the DBA finds. And that's simply like how much more memory do you allocate that extends. And then when that runs out, you extend again. So that's usually a chunk of memory. Okay, so then we call that extends that whole block of memory. And then table space, file group, I mentioned all this, okay? Like tables that are commonly used together are also stored together. So that way the system can easily find it all in one place, not across 2 different disk drives, for instance. And then this is what I initially said. In this part, this is called the data cache. It's called the buffer because this is also where too much calculations happen. All the results are waiting, but then your client cannot handle it. Your phone cannot scroll that fast. So then there's a protocol established between the client and the data cache to send data in little pieces. So until then it holds it. It's called a buffer. Just to temporarily hold data. So it's called a buffer cache. All right. So then, then the other counterpart of the cache is the procedure cache, aka SQL cache. This is the one where the SQL is actually stored, not SQL, but actually compiled SQL. So compiled SQL, and then some kind of key, like a hash key that says when a new query comes in, then I'll quickly find the hash key. I'll summarize that new query and compare that hash key with all these hash keys I already have to see if the exact same query exists in compiled form, like a key value lookup. The key is a hash key of an actual SQL query. Value is the compiled version, compiled meaning the optimizer compiled it, the version. The whole point is if I issue the exact same query, the same black t-shirt I'm looking for, then maybe the system can very simply run the black t-shirt query from here, not involve the optimizer at all. That's the idea. So simplify it. On the other hand, if the query changes, then you have to cache it again. Okay, so that is the SQL cache. Therefore, there are two caches, data cache, SQL cache. SQL cache is not emptied. It's always holding on to compiled SQL. This, on the other hand, comes and goes. Once your transaction is done, that's basically being overwritten by the next transaction. So data cache changes all the time. Once the client gets back all the results, no need for the data cache. It's a waste. So listener, user, scheduler. So we have seen all of this. Okay, in this, for this chapter, the main thing is optimizer. It actually looks at the SQL query that you write, like your homework too. And then maybe it tries to rewrite parts of it, like an optimizing C++ compiler with an aggressive, O2 level optimization. It can maybe unroll like a for loop, or it can take a variable that maybe does not need to be in the for loop, and then maybe move it outside the for loop. It can do all sorts of things that you don't know about without changing the semantics of your code. Likewise, SQL queries can also be changed somewhat. And then this notion of optimization. So here's where we said we can optimize like what the actual backend, what the DBMS does based on all these things, the mode of operation, timing, type of information. This is all review, okay? So we won't spend time on it. The notion of automatic versus manual. You can set one or the other. These are all set by the DBAs, and you can play with these different flags to see what works. There's no one single solution, which is why the choices even exist. BU and need to change the solution over time. And then static versus dynamic. Okay, so then I told you this. Then I also told you about statistical versus rule-based. Here's where we made the comparison between like an expert system that is all rule-based and then a machine learning system that is all data or statistics-based. So the same kind of a difference exists here. So here the query optimization is based on some DBA that has seen the same kind of data for 10 years. So they know exactly how the data is accessed. Then they can come up with a good access plan, and they're probably right. On the other hand, this is actually based on the real data access itself. You can study it and then find out what is better than what, and then use the better version. So they both have the merits, okay? All right. And then, so what do you mean by measure statistics? Now going to this, so what kind of statistics can you measure about some running query? You can measure all of these. So for a table that is involved in the transaction, you can get data such as, how many rows are in the table, and then how many actual physical disk blocks, the hard drive blocks. And then row length, so how many columns are in each row, and then number of distinct values. So this is also very interesting. So each column can have different values. So how many are those? Suppose the column is like biological sex, male, female. The column can only have two possible values. If the column is like a GPA column, 2 decimal GPA, technically you can go from 0.00 to maybe 4.00. That is like 401 different values. If this was date of birth, you can approximately have 365 values and so on. So that's also useful. And then max and min for each column. And then this is the most useful of all. We'll do indexes pretty soon. Are some columns indexed? And if so, those are like highly useful columns. So those are called table statistics. And then speaking of indexes, which we haven't done yet, what exactly are you indexing? And then how many different keys exist in the index? So interesting, okay? So we're gonna look at all this. And then environment. So this is about just simply the actual disk drive data, like almost metadata. But all this can be combined into finding the very best way to access data. For instance, if indexes are available, then definitely that's prioritized over columns that don't have an index. Okay, so this is all like gathering statistics. 3 kinds of statistics you can gather. And then the actual statistics gathering command is actually a SQL command. Like on the console, you can click this or click a button. So compile for Oracle, analyze for MySQL, update for SQL Server. Just minute differences in how you say it, but then they'll all do the exact same thing. So then we quickly come to this query processing idea. In other words, what exactly happens to the SQL query that you write? So the first thing that happens is, the listener will do this. It's parsing the query. And then eventually the idea would be to get the most efficient access execution plan. This actually means table access. So this is when there's no more SQL. There is actually a table name. And then there's actually row ID, physical row ID for the table, maybe even disk drive name. All of that is called the execution plan. You can think of this as compiled version of your C++ code. If SQL was like source code C++, then what does the assembler for that look like? Or what does the machine language version of that look like? We call this the execution plan. There's a SQL query. Yeah, it stores everything. So once you come up with a plan, it stores the whole plan and then like a key for it. Yeah, definitely. Because it will not reanalyze it for any reason at all, which might be a good or a bad thing. Say the statistics have all changed. Okay, so the whole table rows have all changed. Then maybe this is not the best way anymore. And so yeah, then so be it. You can always invalidate the cache, by the way, and then do it one more time. All right. You can do some kind of no caching scheme. The scheduler is a very different thing. The scheduler is all about scheduling transactions, okay? So these all operate at this transaction level. Because remember, this diagram is the whole DBMS, okay? It is not just only for running your query. It's like everything. So these other things are all about transaction management, like serialization schedule. Is it something serializable, deadlock breaking, lock assignment? That's what all of this is. So the thing that we're talking about from now on is just optimizer data cache SQL cache. There's no other process involved. Cool. Okay, so then go back here. These are good questions, by the way, because it means you're thinking. Fine. Yeah, so then parsing eventually gets to an execution plan. The heart of it is this, okay? So this is execution. DBMS executes the query using the chosen execution plan. This means several things. On the one hand, it means take that execution plan and go to your actual disk drive and read all those table rows and columns, and then come and put them in the data cache. And after that, actually run the calculations on the data cache. Say you're looking for GPA more than 3 and CS department students. Then all the data, all the raw table data ended up in your cache. Then some kind of for loop is going to happen, and then it'll look for major equal to CS and GPA more than 3.5. That's all become some kind of low-level programming language, that the driver does. But that is the execution part, and then your actual answer is ready. So you write in SQL, then they'll compile your SQL and execute it for you. That's the idea. And then fetching, so it's a weird name. So fetching fetches the data. It means it gets the data from the data cache, and then sends the results set back to the client. Okay, fetching like this. Okay, so this diagram is quite useful to understand. So look, all right, so everything starts here. You issue a query, like your homework, and then the initial parsing happens, access rights, all that validation. So and then even optimizing. So we call all of this loosely parsing in the sense of going from source code to compiled version. So now you have an execution plan. You have actual disk names and drive names and table row IDs and so on, pointers to all of that. It's all here. So then you cache it, okay? So the first thing that you do, if this is the first time you've seen that query, then put it in the SQL cache. So that is done as a key value kind of a hashing. In other words, I can draw a little big picture there. You would make some kind of a digest, like an MD5 algorithm or some kind of digest, which just means this: you have a unique key that is generated from exactly that SQL query. Surface normals. Get rid of this. All right. So it means only the query that you wrote. You can even change the column name, the hash key would change. So only exactly that source code could have generated a so-called hash key. Imagine you have a hashing algorithm, like an MD5 hashing algorithm. So then the first thing is you give the whole SQL query to it, including all the formatting with the white space, everything. Then you get a so-called key, which is the message digest, okay? So this key would now be used in the SQL cache as the key, and then the access plan. So separately, this all completely analyzed, decomposed and probably rearranged. And then you come up with the most execution access plan, which means you go on the disk and get the data in the most efficient manner possible. So this access plan is now stored as a value. So then say I execute a different SQL query. Then that SQL query is also made to go through this, and then the key is generated. So say the new SQL query's key is called K2. I first go here and see if that K2 is available in my SQL cache or not. If that is also a new key, I've never seen that SQL query before, then I put that in my SQL cache as a key, and then for the value, the new optimized version, the new access plan for that K2 key. So that's tomorrow morning I come in and I do the exact same K2 query again, meaning I do the same SQL. Now the cool thing happens. It'll generate the K2 key, come here and say, hey, this is already available, so this should be the most optimized way to get it. Just go and execute it. That is the idea of this whole SQL cache, okay? It's all done through like a digest, which is the key of the source. In other words, you don't want to store the source and also the compiled version. You could easily do that, but that'll be a long time to match exactly what is in the source with more. Instead, you can easily match with the digest key. You probably know about these hashes, okay? MD5, SHA. There are so many so-called hashing algorithms, and they all produce unique fingerprints. They all produce unique keys that can only come from the one document. Even if you change like one space or add an extra space in your query, then the key would change. So it has to be basically the exact same key. All right, which for us usually comes from a UI. Somebody clicks something in a form and clicks send. So it's probably the exact same SQL. It's not like somebody modifies the SQL by hand, okay? All right, so that is all this part. So it caches it if necessary, otherwise just serves it from the cache. Okay. So now that there's a cache and an access plan, from now on, it's all about the access plan. So you're reusing some access plan, or you just created one brand new and you cached it. So the access plan is the one that actually has like exactly, it knows what to do for your SQL query. There's no select from all that anymore, simply just like input output. Then that plan is executed. That is called the execution phase. So the execution phase consists of going here and then using this as efficiently as possible, and then putting it in the data cache. And then afterwards, doing your actual query, like whatever you wanted here is calculated from here, not from here. That's all here, okay? Execute IO, locks for transaction management, retrieve data blocks. So the main thing is retrieve data blocks. You're actually getting the data and place the blocks in the data cache. And then the main thing that they forgot is execute the query. There should be a new bullet point that says, make all that actually happen, like over here. Big deal, right? After that, we call this fetching. So fetching is when we give you the result set back to you, okay? So then you fetch the results to the user. It's like a pretty odd way to say it, generate result set. I mean, in a way, I guess this should be like over here. That is the actual execution, okay? Then you have the result, give it back to the user. Okay, so then how does that actually work? The parsing phase, again, query optimizer, smaller units. This is when, if possible, the original query is transformed into a slightly different version. Obviously, the engine does not know itself SQL, okay, but it's trying to look at your code to see what it did. The reason is it wants to make it more efficient if possible. Again, in things like C, C++, you have optimizing compilers, right? So how does like, level 2 optimizing work? That's what all it is, optimizing compiler. There's a whole science to all of this, right? So you probably know about this, like optimizing compilers. Yeah, that. How do you do that? It's very cool. Like a whole bunch of heuristics, that people use, and yeah, like loop unrolling is the easiest thing that we always talk about, but there's much more actually. Okay, so many in the, for example, Java's virtual machine event does that. It's called the hotspot compiler. So they're constantly trying to optimize, like how things happen, and then over time things actually run fast. In the C++ compiler, though, it does it at compile time, meaning that the executable that you get is already as optimal as possible. You can read about all this. There's all kinds of talks on it. Okay, so it tries to do that. And then, okay, access plan. So in the end, after doing all of this, this is, like I said, the final deal. So now you have machine code you're going to run. It's DBMS specific, so no two access plans are the same. You can take your same SQL query that you wrote for your homework, go to Microsoft SQL Server, go to, like anything else. You can go to SQLite, you can go to Oracle. And then they all have access plan commands, which I'll show you pretty soon. You can type, generate access plan, show it to me. You can compare the access plans. They're all going to look different. Hopefully, they're all optimized within like their own system, but across each other, there's no comparison. They look different because it's all about binary IO. Like in other words, this knows exactly how the tables are stored. Are they using linked lists? Are they using hash maps? Is it a dictionary? What? Arrays, good old-fashioned pointers. Who knows? But that knows. So you have to do it for your system, and it's going to be damn fast. That's basically the whole guarantee. So then one more time, this is what I already told you. If the access plan already exists, DBMS uses it. And how do you know that? Because you take the new SQL and then compile the hash, compute the hash for it, and go and see if the hash key already exists. If the key exists, then serve the value, and the value is the plan. Just simply output it. This is pretty much what like a web server would do, like a proxy caching web server, except it is not serving DBMS. It's not serving data. It is serving HTML. So before they send you like the next version of CNN.com, right? The headline, suppose the headline didn't change. Then the proxy would actually send you the headline it already has. But say the main headline changes in the backend origin server, then they'll send the proxy server the HTML content and also a new key. The key sometimes is called e-tags. So then you use the e-tags key to compare to say, should I, invalidate my cache or not? Or can I use the cache that I already have? So this idea is a quite popular thing to do because you're not trying to tax the backend too much. Like why force the optimizing compiler to come up with the exact same optimization again? You've already done it. So just use it, reuse it. And then, like I said, all eventually leads to execution. This is really why you do the entire thing in the first place. This is what, by the way, big data, data science, even machine learning, business intelligence, your homework too. In the end, it all comes down to data execution. This one, your query is actually running. Well, so it's going to run. It's all about I/O, like table reads, table writes, and then calculations, and more table reads and more table writes. And then your database is probably changed. Or if you're just looking stuff up, your database does not change, but the user gets results. So locks are acquired. See, the lock manager gets into it because you need a lock specifically, especially for writing, right? You need like a write lock. So all that is considered part of your execution phase. But then when you have all locked is clear to go, then you do get the data, and then it goes in the data cache. And then when they say transaction management commands are processed, it's processed on this copy of the data cache. The actual DBMS tables are not involved, because that's not their job. They just serve data and then they go back to serving more data. Okay, so what does execution mean? I try to explain. It means to execute the access plan. So one last time, this really is it. This is the reason why you do everything else in the world. You want to execute the access plan. You fetch and you send data from the backend database. It is not, yeah, so this execution is not about executing your query. That happens afterwards, okay? So when they say execute the plan, they only mean like up to here. So now the plan is executed, and then afterwards your command can run. Okay. Still compile, obviously. So then the query execution occurs in the fetching step. Then that is called fetching. It's like a weird thing to say. So fetch means, I guess, compute. You fetch the result, you compute the result. Like your query, actually. All right, so then you fetch, that means you compute your result. Say it's a table that you wanted, and then now you have your table. The table is called, so it's in other words, select something from something, where something. Now you have a smaller subset of your table. You call it a result set, like the XML result set we saw earlier. And then you go back to the client. And the client can get raw XML, can get JSON, can get HTML. It's like whatever, it's in between the database and the actual client. It can be a web application server in the middle, or raw data is sent back, and the client has to render it. This is where all the frameworks come in handy, because say you have a framework, Vue or something, right? React, like all of those, right? So those things can actually automatically run. So you set up the client UI so that as soon as the model is changed, then the UI would wake up and just render it. So you don't even have to, set up any extra JavaScript for that. Okay, so then that is all done one way or the other. The client sees like what they want to see. And then DBMS with temporary table space store temporary data. Right, so this is again all part of this loosely called what you call data cache. A part of the data cache might be now used for the next query. So somebody else, has like doing all this, what would they take it? But some of the data cache is still holding on to your data because it is not done sending the client back. Say you search for like 10,000 results. You're only able to scroll at a certain speed, right? So then at the speed at which you scroll, then the client is asking for more and more data. Show me the next page, show me the next page. So they're streaming data until you got everything that you wanted. Till that time, the data cache is holding on to your results. So that's what the slide was saying here. Oops. It may store temporary table. Then they call the table space, okay, temporary table space. So then this is what I just told you. The server, the thing that takes the data back to you, it coordinates the movement of the result set rows. If your result set rows are too much, and then your phone is not able to show all of that, then you hold it in the cache and then send it like piecemeal. That's some kind of protocol that they establish. Okay, so then you can get all your data. That's the fetching. It's all called fetching. So now the user got results, okay? So this was a whole quick, but just full, complete summary of actually what happens. So one last time, right? There's a brand new query, and then you try and see if it already exists. If it doesn't exist, then store the hash key and then store the compile plan. And meanwhile, obviously create the compile plan. On the other hand, say you make the query and the query already exists, then no need to compile it, it's already there. So then you take that and then go here and get data and then do the so-called fetching, which is compute the data, compute the result the user wanted here, and then find a way to send it back to them. So it's a whole loop. Okay? Is it possible? Yeah, I'm sure it is. So one private question was, can the cache run out of memory? These caches are massive, by the way, these days. I would think there are terabytes, like massive cache. And they're also high-speed memory, because this all has to be, it is possible. See, if that happens, then the worst thing is, some of the queries actually would like lose data and you would have to do it again. So yeah, possibly cache can run out of memory. You don't have to have a lot of memory, absolutely. I mean, think of Amazon, okay? So if obviously one machine in Amazon is not doing like all of this. They do geographical proxy serving. So anybody in Australia would go to maybe like Japan or something. But even within like one zone, yeah, they have a massive amount of data cache. Because so many people are buying things from Amazon Prime at the same time. So then you have to try it.
Hi, Professor. This is Andrew from the Den staff.
Okay.
I'm sorry to interrupt you. Would you mind waiting just 30 seconds? I want to change a setting on the encoder real quick.
I definitely wouldn't mind.
Okay, and then I'll let you know when we're good to start again.
Okay,
thank you.
COVID vaccination going on. And look, yours truly is getting vaccinated. OMG. So this happened to me yesterday. I got the Moderna vaccine #1. Oh my God. So then, in a way, it's me.
All right, Professor, we're good to continue.
Oh, thank you.
Thank you for waiting.
Totally. Why not? So I should show you what the heck it looked like. That's what it looked like. Oh my God. What the hell? And if you zoom in, that says Moderna. It's real. here. Cool. And then, so this was, thank you. This was a full cycle, right? So you went from your query to, getting optimized and getting compiled, and then your data got fetched, from the disk, and then executed, which we call fetching, and you saw your results back. So that's neat. And the question is, what can slow all this down? What does the fetcher use to identify which particular subset of records? Yeah, there's definitely pointers like all over the place. So parts of the cache, right? There's a block of memory that's basically allocated to your whole transaction. So everything that is stored in your transaction in the cache would all be off of that pointer. It's all relative data off the pointer. So that's why once a transaction is fully done, then the whole pointer and all the memory that it's pointing to would be completely reclaimed. It's a whole block that is allocated to you. So it'll use that pointer to identify. It's also a nice question. These are great. If you like all this, right, I think you can definitely go look at things like the QBRID, the engine that I've told you in the past about. There's probably many ways to do it. One easy way to do it might be to actually use the MD5 hash key actually as some kind of a key even. But I would think it's actually a hardware address that you're actually getting it. Yeah. There are very rare courses offered in some schools, definitely not USC, on what you would call database implementation. So database implementation is the exact opposite of this course. You will see all this from the other side. You would see, like, how does log management work? What does distributed caching mean anyway? Or what does, two-phase commit mean? You will write code for all of that, right? It's pretty neat. Yeah, we don't have that. A few examples where examples for what you mean, like for the fetching, or because I try to show you guys like a lot of examples, and I'm all about examples. But please tell me specifically what you mean. I'll try and find you examples for sure. I can show you access plans, by the way. In fact, at the end of this lecture, which is actually coming up soon. Yeah, I'll show it to you for sure. That I actually give you like a whole 300-page, I think, like SQL book or something, and that has it. Or there's a smaller booklet that I have that you can look at it. Yeah, they're very cool to look at. They look like compiled, version of your source code. That's really what it looks like. And then there's an art to reading them, by the way. In fact, you can actually edit that. So the crazy thing is you can edit the access plan and then have the machine run your access plan. And that's like low-level operations. If you get really, really smart at, running a certain kind of query over and over, then you can actually do better than the access plan sometimes, which is exactly what machine level programmers do, right? It's assembly code. They can look at machine code, assembly code, and actually do a little bit better than what the machine does, because they know, like, at the higher level what is supposed to happen. So those are fascinating things that you can edit the access plan after all. All right, so these are very obvious things. This should be true for anything in the world. This could be true for Photoshop. My Photoshop is running so slow I cannot, open my huge GoPro, camera video that I took. Well, make all this better. So it's the same idea. Definitely get lots of, CPU with multiple cores, and also try and not run other processes in the DBMS, because then the other process can basically kill your whole DBMS performance. So keep it purely as a DBMS engine. So kill, just move all these processes somewhere else, but get a faster processor with more cores. And then most certainly, as much high speed in RAM as possible, because, again, otherwise it's going to go to disk and start doing paging, which you don't want. And then speaking of the disk, this is the disk where all your data is stored. So have as much high-speed RAID, fast memory as possible, but only for things that are used all the time. The opposite is true. If some data is hardly used, you would put them on tapes and actually have tape robots that fetch data. You've probably seen these, right? They're actually tape robots. Just say tape robots data fetching. It's fascinating what happens in like backend server rooms. There's automatic ways to actually get data. It's going to be very slow. That's actually what happens with tape robots. So they will, get the data for you. Literally an arm will reach out and actually a machine would like load that. That's what's happening. It's crazy that it works. So therefore, this is not high speed by any means, but you would only do it for data that is not accessed all the time. So it's all highly fascinating what really happens with the backend. I'll quickly just run through this and we can move on. Yeah, those robots are amazing.
P1080L.
Okay.
Now, 5 minutes.
So the tapes are all here, and then this robot basically just goes up and down and can move sideways. It's like an XY plotter, but then the arm can actually grab, a tape drive and then mount it for you. It's crazy. This is ultimately how data computation happens. Whoa, tapes, they're all magnetic tapes. Whoa, yeah, locks onto it, pulls it out. Very amazing. Yes, that's what a tape robot was. Therefore, even that you would want like the very best data possible, because the user doesn't want to wait too much. So and then network. So obviously, if you have very high speed, networks between the DBMS and all the clients, then obviously data is going to get out faster. So these are all very straightforward things. This is the part that is under our control, the external. Yeah, that's actually what I thought, believe it or not, right? The noises that it made. It's almost like, a universal computing machine. So then therefore, application code. You can write, bad UI, even that can slow you down. And then you can have bad table design, unnecessary fragmentation, too much normalization. Or you can write bad SQL. So what does bad SQL mean? So I'm going to show you some examples of that. All right, so in the meanwhile, like a little segue, because good SQL will actually use indices. What is the notion of an index? That is one major topic in databases we never brought up so far. Indexes are useful even in a NoSQL world. So in the new NoSQL databases, those data rows can also be indexed. So it's good to understand what an index is. An index, first of all, is exactly what you find in the back of a book. So you take any book at all, like your database book is like what, 1,000 pages. You want to know every single page number where the word normalization is mentioned. If there was no such thing as an index in the back of your book, you are forced to go through every single page literally in your book and spend like many hours and trying to find the word normalization, literally that's the only word you want. And then you will probably look up some other things about normalization, meaning read the paragraph where the word occurs. So imagine, suppose no book, came with an index. You would be wasting so much time looking stuff up, right? You'll probably never look anything up. You just give up. On the other hand, indices are great in the back of a book. So then it's alphabetical. The key thing about a book index is it is all alphabetically stored. So any word that you want, you very easily do like a binary search, right? Meaning if you're looking for the letter K, then go roughly to the middle of your index and then, do back and forth. Within just a few steps, you'll find the word that you want. But the main thing that happens with the index is you find the word that you want, but also helpfully, it gives you page numbers, okay? So say you want to find the word handset layout. That is really the value of the whole index. It is alphabetical and also tells you see the page or the pages where something occurs, okay? This is exactly what happens in a database table. So imagine you have a database table, say you're Amazon. You have 100 million customers. And the table, if you could look at it all, the way those 100 million customers are stored, it's not alphabetical in any way at all, okay? Not by the name, not by the state, not by anything. They're just simply row IDs of people that joined Amazon, okay? But now imagine you want to sort them by the state where they live. Because imagine in Hawaii, all of a sudden there's a recall for car seats. So something bad went wrong in some cars sold in Hawaii. So they want to get to all the Hawaii customers that ordered car seats through Amazon, and they want to send them like a recall email that says, please take your vehicle pretty soon as possible. Then they'll replace it for you for free. So how do you find among 100 million customers the state abbreviation that says HI when the index doesn't exist? You would have to literally go through all the 100 million rows one at a time and then pull out all the ones that say HI and then mail those customers. Okay, so it's like a nightmare, right? Just imagine. And this is the truth. But on the other hand, suppose this exists. Supposing you pre-sort it, you spend some time, and then you make a new table called an index. The new table index is just simply alphabetical. In other words, the index consists of, again, keys and values. So now the keys are state names. So it's like this. So index is a new table you have to create, okay? That's the only cost, really, storage cost. It's a new table. In the new table, things like Alabama, so Arkansas and so on, right? So it's like right here, Arkansas, and then Alaska. I already mentioned Alaska. So, and then maybe like Georgia, California is here somewhere, Hawaii is here, okay? And then things like, Tennessee, Texas, they're all here. All the states, Utah, they're all here. This is alphabetized, first of all, because that is how you create this index. So we call this an index. Then we go through your 100 million. Absolutely. That is exactly right. So what Yash said is totally the point of indexing. You maintain an extra table or many tables. This is just one column, right? A state column. You can have different indexes for different columns in your database. There's an index creation command. You can index GPAs. You can index people's last names. You can index the department where you go to. You can index your school. You can index anything at all. Yeah, that many tables. But those tables are going to massively save us query time. Okay, I'm going to tell you. Suppose there are 100 million rows, 100 million rows. Here's a column called state. And these states, the state column, these two-letter abbreviations happen in any order possible. It's not ordered by any means. Yes, see, you're asking all the cool questions. I love it. Yeah, so CJ is absolutely right. Primary keys, you don't even have to tell them to index it. They index it automatically. Very good. Yes, correct. Time is more important. You're right. Disk space is dirt cheap. So everything that you guys are saying is perfect. Okay, so I want to find the Hawaii customers. Okay, I want to find these guys. You have to go through all the 100 million, because what if the last customer was also from Hawaii? There's no organization whatsoever. But now look at what happens here. I do that. Okay, I spend the time to do it. But every time I see somebody, I take the actual row ID, say this person is Hawaii. I put them right here. So Hawaii, row number 1 is Hawaii. Then say the second person is California. I'm going to put them next to California. Say the third person is Michigan. Then I go to Michigan, and I'm going to put number 3 there. So it's a key value pair, where the key is what you're looking for efficiently. And the value is actual row IDs. So the values become pointers, okay? That is amazing. So now tell me, maximum how many lookups do I have to do to find the Hawaii customers? Just give me an integer. How many times do I have to look through this table? Assuming you don't know, I know exactly where Hawaii is, but I know how many rows there are. I'll even tell you, you can assume a maximum of 64 rows. There are only 50 US states, okay? Plus add things like, Puerto Rico, Virgin Islands, right? So you don't have to, yeah, exactly. In the worst case, well, that's actually a good answer, but you can do better than that. Yes, so Harsh is correct. In the worst case, you need to look through all the 50 till you find it, right? Exactly, but we'll do binary. So tell me then, what you would do. I would literally look at the first row, look at the raster, look at the middle row, and then say, is Hawaii here or is Hawaii here? Suppose Hawaii was here, then I need to only look through that 32. I already threw the other 32 away. And then within there, I would do a binary again and say, should I look through this 16 or this 16? Cool, right? It's actually log n. Log meaning base to logarithm. In other words, 2 raised to 6 is 64, right? So I need to only look up a maximum of 6 back and forths. That's incredible, right? How do you go from 100 million to 6? Okay, so that is the massive speed up that indices give you, believe it or not. It's wildly cool. All right. So when a new customer signs up, say a new customer, they sign up from all states, then you can trivially go in and take those actual row IDs and keep updating your index. So your index does not have to, go out of, it cannot become inconsistent. In the worst case, you can delete your index and just regenerate it. It's going to take some computing. But that is the magical part about this whole binary organization. It's so cool. And this is all stored in reality as a B tree. Okay, there's an actual B tree. And so then the B tree would actually take you through, like back and forth, this way, what. And then finally, all the leaves would be the actual states. The leaves would then have pointing to like some linked list of row IDs or something. So there are many ways to actually organize it. But then the conceptual idea would be that I took something so crazy and I made a very simple index out of it. And that saves me an incredible amount of time. So I trade some pre-computation time to create this. And I also trade some storage space to hold onto it. But then at runtime, when somebody wants to execute queries really fast. This is all done even for, by the way, data science kind of things, meaning big data is also indexed like this. So when the manager, the business intelligence person, the analyst is trying to zoom in and out of data, you're not looking through raw data at all. You're always looking through indexes. So it goes quite fast. How many customers are associated with Hawaii? Can we not query the index with Hawaii? Yeah. I mean, that's basically what you're doing, So there's no primary keys. You could, if you want, you could definitely at the implementation level, you could most certainly do that, okay? Then that means you're just indexing this using one more key. It might be easier just to look through this, knowing it's alphabetized. That's an implementation detail, but you're right. It's still faster than raw. It's called raw table scan, by the way. So raw table scan is always slower than an index, okay? So you can now start to Google all of these. You can say raw table scan, okay, versus indexing. And you will see all kinds of cool things you can read about. Versus index, exactly like that. Just read this, okay? A scan is the opposite of seek, okay? So index scans. Yeah, so it's all the things that I tell you. There might be different diagrams to show you. Nothing quickly that I can point to, but it's that idea. Okay, it's just like this. Anytime you have like some kind of an index, then the mapping is really how you take that index and make that into a tree. You're just saying the same thing in different ways. But in the end, you would not look through your raw data at all. So like here would be an example. So you take like even employee IDs, right? And then somehow like find a way to like index them so that you can very quickly look them up. They're probably indexed, I shouldn't say probably, the registrar's database definitely has an index on student ID, which is why when you type your 10-digit ID, you put it in, you're not looking through all the 40,000 students to find you. It is simple numerical ID, right? So you can easily sort it. And so then they're able to find it quickly. So with indexes, writes are slower. Not necessarily. I mean, there are two different things in the sense. Once the index is created, the index is just simply a way to find a row quickly. As long as the data doesn't change, index is irrelevant. The writes still happen on the main table. Say the Hawaiian customers, buy something right from Hawaii. Indexes are not involved at all. Indexes are only involved when you want to use that state column to find Hawaii people. That's all. So then say somebody leaves Hawaii and moves to Maine, right? Then you need to then do the exact same operation on the index, take the customer, the row ID or something and change it. We're updating the log indexes. Yeah, right. So updating the log index is actually very interesting. Yes, totally. Indexes you can insert, right? In the state example, there's nothing to insert. But say you want to actually insert something here. Yeah, you can definitely go in and find like where you need to insert and then insert a row. In reality, these are all linked lists, okay? So then you already have something linking to something. Say this is linked to here using a linked list. Say these two are linked together. So we're linked here, link here, these are linked. Now all we're saying is to insert like a new row, a new index row, then make a new index row for that, break this link, and then repoint it. Literally do like a link insert. Okay, that's where you can insert a row. Correct. Yeah. So then for that you need to find some kind of an optimal way to do that. In the worst case, by the way, you can also just do this linearly, right? If they're all just pointers, you have the head pointer, then you will know where to insert by just simply traversing all the pointers, looking through all the state names. Say Puerto Rico all of a sudden becomes a state. That'd be pretty interesting, right? Then you'll have PR, and then you'll have 51. Then after Pennsylvania or something, you have to go and insert PR. But that's a one-time operation for US states. But people's names, etc., then definitely what you're saying is true. You need to, do like a good way to access it, and then add like a row. In any case, the main idea is that it is alphabetical. There's some fast way to find it. If it is not easily alphabetizable, suppose it's a street address or something. I should ask you this. In fact, there's a hint. The hint is, well, there's a hint. Let's say there's a hint. The question is, how would you somehow index street addresses? I mean, that's like a weird thing to do. Or not even street addresses. Say there are event names or something. Okay, there's some kind of event name. And event names are quite long strings. They still have a maximum, but there's quite long strings. And the strings are not easily indexable, just straightforward using that as a key. So what would you use as a key? In other words, I want to sort all these somehow, these addresses, they go as values here. What would you use as a key? Exactly, hash, fantastic. So that was the hint, okay? Just like you cannot store raw SQL queries and execution plans. You take the raw SQL query, which is like a long string anyway, and then make like a hash MD5 digest, right? And store the hash key. You do the same thing in here. Suppose this was a long string of event name. Then don't use it as a key, hash it, and then use the hash as a key. Then when you want to search for something, you do the opposite. You do the same thing. Then take what you're searching for, hash it, and then go look for it. But here the hash keys are sorted, so you can find it faster than in the raw table. Hey, cool. Okay, good answer. So we are moving on. So it facilitates searching, sorting all of them. Okay, so it basically is useful in all kinds of SQL queries. Okay, like when you're searching, this is when the main thing happens. Wow. Okay, supposing, in fact, I'll tell you all that here, then we can easily go faster through all the slides. Supposing you have students here, 40,000 students again, all the US students, all in one table. This is your GPA column. And student IDs, here, right? Again, this is the main table, so nothing is sorted, not sorted. GPA is obviously not sorted, all kinds of GPAs. But like I said, in the very worst case, somebody has an absolute 0 and somebody has a 4. Say they just happen to be at the top and bottom. But in the middle, there's all kinds of GPAs, right? You can actually index that table based on GPA values because there are only a finite number of them. There's only 401 values, okay? So I can make a new index where the first row is every student that has a 0 GPA, all the student IDs, and then everybody that has a 0.01 GPA, okay? But then here come the more interesting ones. Say you have somebody with 3.4 and then everybody with 3.4 and then everybody with 3.50, 3.51, all the way up to 4.00, what. So now the registrar says, show me all the top performing students. So you write the SQL query. From student table, like select like student last name, first name, and department. From student table, where GPA more than 3.9. If you go in the raw table, you have to look at every single student and see if they're more than 3.9 or not. Here, the amazing thing is I can just find where 3.9 is and return all of the rows after it. In this case, it's not a one row return, but the entire section of your index, meaning all the students, by definition, all got more than 3.9. So that is where these indices are incredibly useful in actual SQL commands. That's what this is trying to tell you. Like they're searching, so searching. And then I don't know what to mean by sorting. I mean, these are all ultimately just ways of saying, even aggregate functions, you want to find, again, the min and max or something. So min is so trivial in something that is indexed. Just go look at the first key and then return all the values. Say it is, going from small to large. And then say you want the largest value, again, in our example, who got like 4.0 GPA. Literally return the very last indexes, all the students. No more going through 40,000 students. So those are very easy. But I'll just store student ID. Yeah, for student ID, there's no need to hash it, okay? I just meant for hashing is for something that is not easily storable. Just want to share a small trick. Okay, go ahead. You can share the trick. Meanwhile, I'll keep going. Ordered set of values. So the whole point is indexes are ordered, okay? If there's one thing to remember, it's that hash keys can be ordered, alphabets can be ordered, things can be ordered. And that is where the power lies. So then what you're ordering is the key, which can be the raw thing in the cell, like state names. Or if the raw thing is too much to store, some kind of hash with that. And then pointers meaning row IDs and actual pointers to actual row IDs. And then it's much, much, much better than doing the full table scan. Cool. Yeah, sure. It's funny you mentioned that, right? I'll definitely show you that. Actually, it's in one of the slides that will show you the access plan. Oh, I see. This is smart. He's literally showing you how bad the plan can be if you don't index it and how amazing it's going to be after the indexing. This is clever. I should actually do that. Cool. But we do have that command coming up, okay? All right, so this is easy. So the reason for using is, supposing you do some computation, it's a one-time cost. The runtime query cost is so fast, vastly cheaper than doing full searches through millions, 10 millions, 100 millions. That's the world these days. So hands down, no comparison, many, many orders of magnitude faster. Here's where I give you a book, a little MySQL book just for fun. It's a nice book. Have fun going through a 1,000-page book. Supposing I did not print the index on purpose, I made the PDF smaller, and I asked you, where does it say the word index? So show me in the whole book where it says index. By the way, you can learn like lots of cool SQL from here, okay? You would have to go through every single page and then see if the page says index or not, okay? It's a nightmare. But then now that we're given the index, hopefully, I can go through the index really, really fast. The power of the index is here. There you go. Say I'm looking for normalization, like, where all they say normalization, the example used before. Just go here. Even though I'm scrolling, right, in reality, if I had a physical book, I'll just flip the book back and forth a few times. This saw, by the way, dictionary is also indexes, okay? The word you're looking for is also alphabetized. So literally crack the middle of the dictionary open and then say, should I look in the first half or the second half? And then for that, I'll again break it in half. So it's a whole log search, okay? A binary search. So normalization is here. We're almost there. This is still faster than going through the whole thing, by the way. So no backend, national, what the hell is it? No number, I don't know, it's somewhere. There's no normalization. Maybe not. I'd be shocked. One more time. Oh, it's NA. Okay, so NA, NO. Incredibly, this very practical book does not care about normalization, it turns out. Oh, that's pretty cool. Well, let's look for SQL so we're not totally disappointed, okay? Like, where all do they say the word SQL? Hopefully find that. Save point scalar. Yeah, it is funny. This book does not talk about normalization. Weird. Select command, okay? Okay, I'll just use that. Suppose you want many, many select examples, right? Where all this select? Here they are. By the way, you can have indexes within indexes. You can even do secondary level indexing. In a book, they usually do that. But this is the power one last time. If the index was also scrambled, then good luck, it's a pain. This still might be easier than going through the whole book, but what is more efficient is that the index keys are sorted. That's it. Okay, move on. This is what the index then looks like. So the example that I gave you is here. In the raw table, there are 14,700 people, and then the states all over the place. See, it's not alphabetical. I see. Well, thank you. No way. Okay. I will click on it so that I'll then put it in extras for everybody. Thank you for that. Neat. I appreciate it. Many years ago, by the way, I wrote a Perl program. So I wrote a RenderMan book, okay? I wanted to index my own book. So I wrote a Perl program that goes through every single page and then finds the keywords that I'm looking for and build this index magically. So I still have that. It just works. Just text processing. Just create the index, meaning you give it some keywords and then it spits out all the pages where the keywords occur. There are people that do it for a living. There are people called indexers, and then textbooks are sent to them and they know something about the subject matter, right? So then they'll use the expertise to index things. Okay, so I was my own indexer for my book. Here it is. This is ultimately what you do. Take all of them and then alphabetize them. Say Arizona. Here they do it slightly differently. Okay, Florida does not have a whole row of Floridas. Here they do one followed by another. But still, for every Florida, you'll have a starting point and an ending point. In other words, you'll have one more table that is alphabetical where it says, where does Michigan start? Like in this table, in the key table, in the index table. Where does Michigan start? Where does Michigan end? Some kind of block of row IDs. Okay, you can do it in many ways. Is the point. But however you do it, those are the only people from Florida, from this little thing that we have, which is cool. I don't have to look through all this anymore. So just keep that idea in mind to retain it. All right, so then what columns are good for doing indexes? Like, do you want to index every single column? Because you can if you want, but is it useful? Then you have some measures to decide, should a column even be indexed or not? That measure of deciding if a column should be indexed is called data sparsity. It's such a funny word, okay? Sparse means not full, it's very empty. But they use the word sparsity to actually mean like a count of different values. So again, low sparsity means male, female. So suppose there was a biological thing that says you have to tell us whether you're male or female. So every single person, unless they're like, like non-binary, kind of thing, right? They're going to say male or female. So in that sense, if you make an index, the index will only have two keys. One key is going to be called male. One more key is going to be called female. And the male key would point to almost half the rows in your database. And the female key would point to half the rows in your database. Not very useful. I might as well go through the whole table myself, okay? That is all that this means. So when the number of different values possible in a column is not very high, then that column is not worth indexing. Male, female column is not worth indexing. On the other hand, what if a column has 300 different values? Then do you think that could be indexed? And where do you think that is used? There's a column that I can think of that has 300 or more actually possible values. And then somebody that we're all pretty fond of and familiar with, or maybe love to hate, indexes exactly that column and is actually quite useful. So who do you think I'm talking about? There's a social media, app that we use every 3 years, where there's a certain column, and the column has a little more than 300 values, between 300 and 400 values. And so then they certainly index that column. And then they use it quite heavily. They actually give it to you every day if you want, when you go there. What column is it? What am I thinking of? Facebook, every morning at midnight. Exactly. Upcoming birthdays, today's birthday. Sure. That's exactly what they do, okay? So they're able to easily index birthdays. And then they just serve them every single day. So every day, brand new birthdays come up, and then they decide, who should be notified. Like the birthday people, who their friends are, and every single friend gets a notification. That's how that works. Cool, right? It's extremely useful. Otherwise, if you want to find, Facebook wants to find out today who was born, they need to go through, 2 billion people. So that's going to be very slow, which is why when somebody signs on, they'll go to the index table that is about 365 rows and add this new person's, profile ID onto the date of birth. That's it. So simple, but it works. All right, so that is sparsity. In other words, things that are highly sparse, things that like low sparsity. That means low number of values possible. This is the exact opposite of what we think of as sparsity, by the way, okay? In my mind, okay, so forget what I want. Low sparsity means too few number of different possible values, like male, female, then don't index it. Date of birth is where they index it. Okay, how do you actually do this table? So this table is abstract. How do you actually build it? So one way is you can build all kinds of B trees, okay, to actually go through this in a binary way. So that's called the B tree index. You can also do something called a bitmap index, or you can do a hash index. So these are all different ways of indexing that. And I think I'm going to show you a bitmap index example because its use is actually bit values. Like within 1 byte or 8 bits, you can even use that. You can use a hardware operation to actually get like a certain column value. Okay, so what data structure is used is decided by the database management system. So they all work, one way or the other. And so then the B-tree index and a bitmap index example. Suppose you are trying to index customers' names, the last name, so you want to look them up really fast. And then you want to find their like row ID or something. Then you would literally create a B-tree of the customer's names. You start with any customer, hopefully some customer in the middle of the alphabet. And then any customer whose letter is smaller than Lee, like in this case, difference, is used as one more like a level. So these are all like, non-leaves. So the leaves are all at the bottom, right? Because it looks Lee depends, they show up here, for example. So that is what you want to do. So and then no matter how many levels you have, You're always going to the leaf because the leaf is the one that holds the actual data that you want, which is the row IDs. But then the non-leaves can be used for quick traversal. So again, like I said, say you're searching for Strickland, okay? So you ask Lee, is Strickland more than Lee, yes or no? Well, S is more than L, so go this way. So now you can throw away half your database. You don't have to look through this part. So again, you're looking for Strickland. Is it to the right of R, to the left of R? Well, S is more than R, so go this way. So you don't have to look at these people anymore. And at one point, finally, we'll reach the bucket, the leaf bucket, where all of the ones to the right of Rob are stored. And now you have to linearly go through them, but only linearly go through 3 people as opposed to 12 people. So it still works, okay? In other words, I finally find Strickland. It took me one operation, second operation, and that scan. So fast, as opposed to scanning all of them in random order. Like imagine I'm trying to look for Strickland. I gotta look through all of these, look where Strickland, almost the very end. So this would be like OIN operation, right? Yeah, so it can be faster. Hey, cool. So that's the notion of a B tree maintenance, okay? You can do that. And so then obviously the B trees can become highly, imbalanced. So what happens when a B tree becomes imbalanced? In other words, this looks beautifully balanced. So there's way more, not this example, but different example. There are many more branches just deeply onto one side, and then the other side, it is like DFS, sure. Then the other side is, pretty shallow, relatively speaking. Yeah, exactly. So then such a B tree actually becomes useless because then it's almost like linear search. You're doing so many back and forths that you might as well look through the table. So the table is heavily imbalanced, okay? Then you do something called rotation, where you might reorganize all these nodes so the nodes can all, come and go. They can be swapped and cycled so that you balance the tree so that you still have the same data, but now your tree has equal on the left and right. So it's called tree balancing, right? So, B tree rotation. You can do like all kinds of things, okay? Just B tree rotation. These are all things that we teach in like CS 104. If you're curious, if you want to go fill in the blanks someday in your life, you can actually do it, okay? Okay. I used to teach CS 104, so this is quite fascinating. So how do you get to CS 104 if you want? It's here. So go here, oops, but then not do like all of it, just simply, just go here. Then you will get that. Ooh. So somewhere in there is actually tree rotation. Cool. Yes. Performance tuning. So let's then finish this up. There's still just a little bit more to tell you. Okay, so all this fascinating. What about a bitmap index? So when will we use a bitmap index? Okay, so supposing there's a street, right? So in many parts of the Midwest, the street might be called something, for example, Wilson Avenue. But then there might be a Wilson Avenue Southwest, there might be a Wilson Avenue Northwest. Because, the freeway went in the middle, then they said north, they said south. What I said actually exists in Cedar Rapids, Iowa. There's a Wilson Avenue Northeast and Southwest. Okay, say this city. Okay. All right. So then what do? Here's what you do. You make a bit for each of those variations, okay, just one bit. So if some customer lives in Northwest, you turn only the bit on and all the other bits are 0. Obviously, they only live in one place. And then this customer lives in Southeast, Southwest, whatever. So therefore, in any one row, the row, by the way, maximum has like 8 bits because it's a byte. And the things you don't use, you pad with 0 because nobody even goes there. But these are the things you care about. In one row, only one of them is turned on, everybody else is turned off. So then you can trivially do a hardware AND with this one, with 0. In this case, let's do just 4 bits, okay? You can hardware AND this table with a bit masked called 0001. In other words, simply search for all of them and give me all the 0001s. So then I'll get this row, I'll get this row, and I can very quickly go and find, what is indexing. Okay? So in other words, these ultimately are used as indexes. Every column is used as an index, but you don't have to go through bit one by one to see, tell me like which one is 0, which one is 1. I can do a whole bit operation on the whole word really. So I'm still looking only for this bit mask, and then it doesn't matter what the other 4 bits are. I'll probably make them all 0s. So then that way, yeah, sure, that's a good point. Okay, so B3, yes, he's absolutely right. It depends on the tree implementation. B3 is self-balancing, but you can set that, I think, to run it whatever in order you want. So then as customers are getting inserted, then automatically you'll be able to see this all like reorganizing. That's very smart. Yes, that's why databases actually use B trees. So what is an example of a tree that is not self-balancing? What other kind of tree would you have to manually do a rotation? Do you know? There's many other names, right? Red, black, AVL, BST. Keep going. Interesting. have a little discussion there. Okay, so what is not self-balancing? Many trees are not self-balancing, but so the notion of self-balancing, I mean, you can just kick it off. Like I said, it's an extra callback even if you want. So you can make any tree self-balancing yourself. In the real world, it's not a problem, right? Because as soon as some data modifies the data structure, then you can actually run balancing. So in that sense, it's not a big deal. But you're right, B trees are supposed to be like self-balancing. So then why do you even need this? So this notion of regions, right? In this case, I gave you an example of one street that has 4 possible values. But what if these are not that? What if these are like, again, customers, but every customer lives in like some area of the US? Suppose you divide the US into all these regions, right? Like East and Midwest and mountain states and then actual West Coast. Then there are 4 different regions and then things like Alaska and then Hawaii, 6 regions. Then I can use 6 columns for that, okay? And then literally just turn the bits on and off. And then I can find people in a region really, really fast like that. That is what this is for. So create 6 columns and then pad the last 2 with 0. So the 6 columns start like this. So then if you want Hawaii, then you look for 0, 1, 0, 0, 0, 0, and then 2 more zeros. Literally like this, okay? Yeah. So Hawaii, California at 001 because California is in our table. This one, Western. So 0, 0, 1, and so on. So Hawaii is 0, 1 because Hawaii actually came before West. Cool. That's what we do. And then this is the main point. So the index itself is stored as a byte. Okay, so a byte is just simply used, even though you're wasting like the extra bits. Exactly, it is extra zeros. You're wasting some space, but it's fast in hardware to search through them. Okay, then when you query for the Western region, so then you would do the AND with a so-called bit mask. So then if you're looking for Western region customers, then that's the only bit that is turned on. All the other bits are turned off. So this operation at the hardware level is quite fast than you manually searching to see if anything is 0 or 1. That is the reason why it is ultimately all done. Cool. So it's called a bitmap index. Then this notion of an index selectivity. So once again, this again goes back to the notion of sparsity. So if you create an index, and the question is how likely is the actual SQL engine going to use it? In other words, SQL engine is not always forced to use an index just because you created the index. If the index actually ends up being like not optimal, then the optimizer is free to not use it. So then it's called a hint, okay? So the hint is something that you give to a compiler, and then you say, if possible, if it is efficient, do this. Otherwise, the compiler is free to ignore your hint. So I'll show you SQL pretty soon where in the commands, using C kind of commands, using /*, not even C++, / command, an old-fashioned C command, you can embed these index names in the SQL command. And then if the optimizer wants, it can use it. Okay, so then that measure of how likely are you going to use it is called index selectivity. All right, so index is used when a subset of rows from the large table. Right, so this is the classic example of Hawaii. So once again, 100 million Amazon customers, only 50 US states. You want a subset of them, but you're not willing to go through the whole table. Then you would use an index for that. Index cannot always be used to improve performance. I told you, if the index leads to one more level of interaction lookup, then there's no need, especially when you have like this sparse number of values, meaning male, female. All right. And then you can also do indexes based on computed columns. It's actually very weird. They're called function-based indexes, meaning, say you have a sales agent, kind of a table. These columns already exist. You know how much money the salesperson is making. And then say there's a commission that is different for each salesperson. One person might get a 10% commission, the other person gets a 4% commission. But there's a separate column called the commission column. But now you want a new column that is salary plus commission. Say the commission was actually dollar figures, okay? Say the person makes $100,000, the first salesperson. Second, and they get a commission of $20,000. The next person is $80,000, $10,000. So these are actual numbers. But now you want to add them because you're trying to find how much they actually make. But then that column, new column, is what we call a computed column. You can also tell the system to index all the values in that new column. That is very cool. That way, if you run some SQL query based on that exact expression, then the computed index column would be used. The function index column would be used for that. That is all this is saying, okay? Then that's called a function-based index. Okay, so what I told you is already here. Okay, ultimately, when our index is useful, so one more time, the indexable column like GPA, Hawaii, all that, appears in a where statement. A having statement, it's like a where statement, but this is used with aggregate queries. Like, don't give me a GPA for like all of Viterbi. So give me a GPA, break it down by school. And then you'll get a subset. But even within that, show me all the students having like more than 3.9. So having is a lot like, where, it's like an if statement. Therefore, indexes come in handy. And then indexable column appears in group by. It's the same idea, okay? If you say group by something, like group by last name or something, then the index can also be used to find that very quickly. And then order by, these are all about sorting, okay? So once again, needless to say, indexes come with sorted data. So you can use it for sorting kind of queries. Cool. And then max and min, so again, because indexes are sorted. All of this is possible for the same reason. Index keys are sorted. So GPAs are sorted from 0 to 4. I want to find the max GPA. Maybe it's not even 4, maybe it's 3.98. But I would know that instantly by going in the GPA index and looking at the last row. Then that's the max. And all the students that got the max. Cool. And then your high data sparsity. So again, this is like an oxymoron. By high sparsity, what they mean is there's many different possible values. So it is worth indexing. That's all. All right, so same thing again, worth indexing with creating indexes on columns that appear in where, having, by, same method, okay? And even joining, okay? Because in joining, again, you're saying join two rows as long as the values are the same. Again, it's about a value. So then I can just quickly go through the index to, find like what should be joined with what. And then, okay, so that was the whole indexing little segue. Now we can go back to like optimization, what the DBMS does, rule-based versus cost-based. Again, this like, pre-done, predetermined, more like a expert system. Then use preset rules and points. So what is the best approach to execute a query? It's almost like different possible table accesses, different possible column, access, what would all come with a cost. So you have multiple alternatives, and then you apply different sets of rules and find out what is the cheapest access plan, like least cost, and then go with that. That is called rule-based optimization. So then cost-based is this one. This one is now based on statistics. Okay, you will actually assign a cost to all of these things. How much memory is it taking up, and what about I/O? How big is the table? How many rows, and what all the statistics. Then again, many different options will give you many different costs, and then you would find the least cost. Even though they're saying the word cost, it appears in both. It appears here and appears here. Okay, but the difference is how that cost is computed. Here, the cost is computed based on rules. Here, the cost is computed based on data, like statistical data that you gather, no rules. So again, like machine learning versus expert systems. Okay, you set which one. And then the optimizer might not choose the best one. Again, so when will the optimizer go wrong? Okay, like when does it not produce the best value? Suppose the statistics are old, meaning your table now became like 5 times as big as it used to be. So what worked in the past is not working now. And therefore, all you have to do is update the statistics again. You can do that anytime. Go and gather statistics. And then this won't happen. In other words, don't use stale data. In machine learning, you need to constantly update your table. If your data is changing all the time, then neural networks weights are all wrong, because the demographics changed. So you have to update your data and recompute. You have to retrain pretty much. Really. Why not create a? So yeah, you can definitely do that. So in Amazon, that's probably exactly what they do. So these are all like just toy examples, okay? So Amazon wants to, do the very best thing. So they'll actually pre-break the customers down and then make multiple tables and keep them all separate. So the notion of indexing just goes away. So totally. Well, there is, so there was a private question that says, is rule-based better than cost-based, in some cases? Yeah, I think it might be. This is why expert systems, by the way, in pretty narrow domains in the world, like oil exploration, still beat the heck out of machine learning. See, it's not all machine learning, okay? If somebody has done petroleum engineering for 30 years, they would know so much about oil wells that your crazy LiDAR data from measurements, there's no way in hell it even knows what any of that is. So the expert wins, okay? So yes, there are definitely advantages. Yeah, so Yash is continuing. I agree with you, okay? Definitely, I'm sure that Amazon does not maintain a single table with 100 million customers, for sure. So now you understand there's more than one way to solve all these problems. But if you don't do any of them, it is a problem. And when a single table has that much data, then not having an index is definitely a problem. Okay, now I'm going to tell you optimizer hints. So how do you, as a SQL writer, be able to tell the optimizer, I made an index and this is what the name of the index is. So you would make comments out of them in SQL command. So technically there are comments, but if you look carefully in the comments, you hide like extra data. For example, suppose you want to tell the system, fetch all of the rows and then do the computation on it, as opposed to fetching parts of rows at a time. Suppose you think that is faster. Then select, so this is actually very interesting, right? So what do you think this says? Select star, see, do you see that? So select star from product where quantity on hand is less than 10. So you're trying to find out all the things in your store, all the details about things, product ID, name, price, obviously how much quantity we have left, minimum order, last order date, vendor, everything. So that star is the real SQL star from product where. But this slash star plus all rows star slash, that part looks like a C language comment. Because in C language, opening comment syntax and closing comment tags. And then that is where your actual hint is. Plus all rows is the name of the hint. You simply say plus to tell the system. It is not some comment that I leave for you and me. It is actually a system comment, meaning it is an optimizer hint. So the plus is simply a secret keyword. Okay, so say plus and then say all rows. So then this is saying tell the optimizer minimize the overall execution time. So do what you have to do to fetch all the rows as efficiently as possible. Because for this query, you're going to need all the rows, right? Yeah. So then you say all rows minimization. Yeah, sure, exactly. So if you do it like this, then there's no indexing required, at least for that column, for the customer location column. True. Okay, first row. Sometimes maybe you want to just quickly get some exploratory data. Maybe the first n rows are enough, okay? So then you want to quickly get a sample. How many products do we have? Anyway, everything's less than 10. So then you optimize the fetch based on just first rows, like first n rows. Cool. So maybe that is a different access plan compared to this one. So you tell it which you want, okay? Because it is based on use case. Here, you want to see all of them. Here, you also want to see all of them, but maybe only just for the top few rows. In other words, this is slowly, incrementing over time. In other words, it's filling in more and more over time. You can just watch what is happening. Here, it will give me like all the results all at once. That's all it is. This one. So I made an index based on the column called quantity on hand. This is actually super cool, right? This means you can quickly query, tell me all the products that I have only 1 left. Tell me all the products that I have 5 left. Good question, it will not. Yes. So the optimizer will not automatically go looking for any index at all. So you have to tell it. Cool. Yeah, sure. Some things, sorry, Iman is correct. If you don't tell it anything, right? So it probably optimizes for that more than this. So maybe there's a no op as opposed to this being a no op. So I agree with you. Okay, so this is quite useful. Tell me all the things that I have exactly 5 left. Wow, I don't have to go through my whole store. The index can tell me. It's quite neat. Okay, move on. I'm a little bit delayed, but not too delayed. It's okay. Performance tuning, client perspective. So again, the idea would be you want to make the query optimization as fast as possible. And then they are DBMS specific, you cannot port them. Yeah, what works, like all those optimizer settings. What works for Oracle might not work for like Microsoft SQL Server. You have to do it again because they're all ultimately based on exactly how the hardware stores your data, binary data. And then this is the part where you and I can do something, and it's very simple what I'm going to tell you. So how can you write decent SQL code, okay? It's a lot like standard programming, by the way. Okay, so conditional expressions. Here's where you say things like, where GPA more than 3.9, okay? Suppose you write something like where GPA more than 3.9, or where salary, equal to 100,000, whatever you're writing. Here's what you can do. In the end, it all comes down to this, okay? It is so simple. If you're able to do numerical comparisons, like compare student ID numbers, then somebody's name, date, etc., those are faster. So what this actually means is, suppose you're doing, and if you can, make something numeric, first of all. This is why student IDs might be numerical as opposed to a string, because strings are slower. So make something numerical. This also means one more thing. So maybe if some column that is numerical can help you go faster, right? Put that test before some other test. Say you're doing numerical comparisons and string comparisons on a different string column. Maybe still put this first because this runs faster than that. So you can reorder them. That's one thing you can do. The other thing you can do is this. This is very simple. It's almost so silly that somebody would do it, but we teach it anyway, which is this. Use only actual column names on the one side of a where query. Like say GPA more than 3.9. Only use actually the word GPA column names. On the other side, only use numbers. This just simply means do not mix up a column name and an actual value. And that's very silly that you would even do that. So I'll give you a bad example and a good example. The bad example would be, so show me all the students where GPA plus 0.2 is more than 3.6. Just like a toy example is a weird example. Do not do that in real life. But we're saying don't do this, okay? Don't do this. The reason to not do this is, say there was an index based on the GPA column. Then if you just say the word GPA, in other words, say you took it onto the other side, literally subtract and make it 3.4. That's an easy query because I can find out what 3.4 is in this binary, ordering, and I can give you all these people. They're all more than 3.0. But if you do this, then the indexing cannot be used, because for every single row, the system does not know what GPA plus 0.2 means. So this mixture between a column name and an actual literal value breaks the indexing. So do not break the indexing by mixing it up. Literally just simplify it. That's like obvious, right? Duh. I mean, I'm going to give you an example where somebody might do it for a different reason. Somebody might actually say, show me all the price values. And then suppose I increase the price by 10%. Then show me all of the things that still cost like $50. In other words, you're trying to make the times 1.1 is what I mean. Like what you're trying to wonder is, I want to know all the products that after I increase the price by 10%, the price would be more than $50. Suppose I want to write a query like that. This is what the analyst would write because it's the logic that they want. But now I tell you, don't do this. It's so easy. You simply divide this by 1.1 and whatever that happens, hardwire that in. Because it's what they're looking for. Like tell me all the current price times 1.1. Tell me all the ones where the price is such that that combined value is more than 50. So this is a reasonable thing that somebody would write in the real world. Okay? Or some current employee's salary times like 5% raise should be less than 100,000. So you want to give people a raise, but then you want to find out who are all the people that even with the raise are making less than $100,000. So you will do it. Yeah, the parser does not look at your expression at all, unfortunately. So yeah, the parser does not do it automatically. So you are supposed to simplify it, okay? It's just a weird, silly, but so it is. And the reason why the parser won't simplify it is because this expression can be quite crazy, okay? This expression can involve all kinds of column names. It can be basically some massive computed expression. So the parser then will not get into simplifying an expression for you. So you need to like do the right thing, this idea. Wow. Okay, so in the end, all that it means is keep column names and literals separate. Okay, yeah. And this is something that we can easily do as opposed to having the parser do it automatically. Okay, so that is what this part was. There's one more thing, okay? So the one more thing is all about, again, like programming, things that can happen, things that can be true and things that can be false. So suppose you say, show me all the students who are, 3.9 GPA and also computer science. Okay, suppose you say that 3.9, 3.95 and also CS, suppose you want to do that. Then there are two ways to write this. On the one hand, you can say, show me all the students where major is, CS, major is CS, and GPA more than 3.9. That's one way to write it, more than 3.9. Or you can flip them. You can say GPA more than 3.9 and major, equal to CS. And there's a difference in how they run, okay? Because you want both of those to be true, right? So there's a chance that this fails. In other words, not many students have more than 3.9 GPA, right? So supposing a student does not have more than 3.95, there's no need to even look for this at all because the whole query fails, right? So what we're saying is any condition that can fail, if you have an and after that, put the failing condition first, because then if the condition fails, then no need to look through all the others and see if they're computer science or not, okay? That is the logic. So things that can fail, put them in the beginning with an and condition. Things that can succeed, put them first with an or condition. Suppose you say this or this or this. If the first one has a high likelihood of saying yes, then we don't have to do this at all. Exactly, you want to check the second, or the third, or the fourth, because no need, okay? I'm saying this or this or this. So one of them is true, they're all true. That is the magic of or. Likewise, an and, if I say I want to be rich and I want to be single and I want to be in Los Angeles, then if I'm not rich, then forget the others. It doesn't even matter. So that is the notion of it. In programming, we do the exact same thing. In programming, by the way, it's highly, again, the compiler has no idea about what you're actually looking for. So you have to actually manually do it, and it will make a huge difference. Likewise here, right there, when your conditionals, again, greater than, less than, especially, equal to the ones. So equal to's are easy to compare, right? Because you can use indices for them. So whenever possible, write equality as opposed to inequality. This all depends on whether you can do this by logical or not. And this is the one where I told you, divide by 1.1, subtract 0.2. So don't just only, have don't have mixtures of column names and literals. So only have literals on one side, column names, as I said. Write equality conditions first when using multiple conditional expressions. So this one, like this, when something can go false easily, put it in the beginning of and, because then the rest would not have to be checked. You can skip it. Likewise, if something can succeed quite often, put that first when you're looking for all conditions, because then you don't have to check the rest. It is all about not checking the rest. And then Don't use not. Because not means you're taking like a whole nice index, but now you're finding everybody that is not that index, okay? It's going to be very slow. So if your logic allows it, then don't use not. Cool. So many different ways of saying what we said. And then in the end, it all comes down to saying, just write decent SQL. In other words, take a look at what you're trying to do. And then, only use the columns that you want, only use the tables that you want, and then find best ways to join them, and then how you would want to query it, and how you want to determine it. In other words, write standard, like good SQL, that's all. The slide doesn't even have to be there, by the way. It just means do the right thing, okay? It just means know what you want and find a good way to get it. Then the compiler can help you even more, like on top of it, if you make indices. All right. Few more slides. Right, so then this is all just like what kind of parameters do you set. So then in the end, there's some kind of config file somewhere, and then you're able to set parameters for all of these. You can find out you can set how big the data cache is going to be. If you waste, much larger data cache, and you find that most of the time most queries don't use it, then you can make a smaller data cache, and so on. Likewise, you can vary the size of the SQL cache. The SQL cache is very small, and if the cache becomes full, then newer queries that are coming in would displace the older queries. You can use a timestamp and delete the oldest cache value that you have, meaning nobody used it recently. But if the person uses it tomorrow, then sadly you deleted it. So therefore, try to have as large SQL cache value as possible. And then this data cache can be broken down into more caches, okay, for storing results, and then things like sort cache. Loosely, I would call all of this data cache, make it as big as possible. And then finally, you can set the mode. Do you want to use rule-based? Do you want to use, statistics-based? Do you want to do, automatic? Do you want to do manual? All that is optimize the mode. That is all in here. And then this is a very different idea. This is actually a very cool idea. Many real-world databases actually do that. You have this thing called in-memory database where as long as the data that is being served is lightweight, like server logs, actually can be stored in main memory when somebody's analyzing them. You can store the actual data, the full real data, so-called raw data, in high-speed main memory, okay? And increasingly, this is getting more and more the norm, meaning, like, Instagram, for example, say some photograph, goes viral, then they can actually store those kinds of photographs in main memory. If somebody searches for them, just simply serve them from out of main memory. There's no backend, there's no back storage, there's no limited bandwidth IO, none of that, okay? That is called in-memory database. Obviously, yeah, the main memory, actually not the, of the DBMS, So if you still have the data all being managed by a separate person in the back end, it's not the main memory there. It's more the main memory where the DBMS was, like this one. As opposed to, the memory here, some memory over here, the main memory part of here. It's called in-memory data. Exactly, so things like MemSQL, sure. I'll definitely tell you about MemSQL in like part 2 of this course. Yeah, right. Well, MemSQL can run in RAM. So this is all correct. I don't mean the RAM. And so then the RAM is actually going to store your real data. Normally, you never store data in RAM, okay? But then RAM can be used to store data. And that is as fast as you can ever look it up. And obviously, you wouldn't do this to your whole table because, first of all, you don't have that much address space. Second, RAM is incredibly expensive. So you'll only want to, yeah, sure. Yeah, Google does it for, again, frequently used keywords, right? When they have trending keywords, there's no need for them to do full-blown, page rank, sorting, like all that, right? Absolutely. If light goes, then I don't know what you mean by that. What do you mean light goes? Can you explain? Sounds cool. Okay, so you have this. Okay, we'll hopefully learn like a lot of neat things. Oh, I see. Yeah, sure, that's true. Yeah, but you can load it again. Yeah, true. Okay, so that is in-memory database, but much more on this coming up. Okay, it's very cool. Amazon gives its customers actually a chance to use it for their business. So your business can be quite fast if you're willing to pay for it. You can do it on the cloud. And this is all just stuff about data storage. So RAID is a pretty cool data architecture from the 80s that shows how you can optimally store data across what are called partitions, okay? So there's like independent disk. RAID looks like basically an old-fashioned record serving machine. There's all these platters. You can simultaneously stripe data, so like this. So you have like all of these disks, then they're all spinning at the same time. And they all have independent like read and write heads, okay? So you can then stream data here, 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 but all of this combined is the data that you wrote. So it's like parallel data writing. Likewise, when you're reading, you can also read data in parallel, as opposed to having one disk spin too much. So that's the notion of RAID, reading and writing. So you can definitely store data in RAIDs. RAIDs are incredibly expensive, okay? I see. That's actually cool. At DreamWorks, we have, it's not a data center, more like a render farm, but same idea, it's storing rendering data. So it's incredible, what the racks had. They had halon fire extinguisher things at the top. You look up, there's a fire, instantly will be sprayed with halon. Yes. And then likewise in foreign countries, and some of these servers might actually be, when power is not reliable, they will have diesel generators, anything to keep all this going, okay? Okay. So we're about 10 minutes late, but it's no big deal. I'll just show you RAID, okay? Because you need to see what it looks like. RAIDs are cool. That's called striping. What I told you, when you write data in parallel, like that, read them in parallel, it's called striping. You stripe multiple disks at the same time. Okay, so I'll just say RAID array stripe. The reason why they all look like tall towers is literally those platters are all like in there. Yeah, like that. So now this is multiple RAIDs. Those are called blocks, those independent platters. Just simultaneously writing on like all those blocks and maybe even these blocks. Wow. So it's like extra RAID stuff. Then you make what is called a storage area network with all of this. They're called SANs. So a SAN would contain like, this whole RAID architecture. I might even tell you stuff like that. I'll just say, RAID stripes, SAN architecture. Then you'll start to see how these are hooked up together. You can even have like federations of them. You can have groups of them. You can have hierarchies of them. I don't need the word stripes actually. So RAID array SAN architecture. And you'll start to see, so this is what I mean. How you organize like all these RAIDs, okay, this is all like a whole art. This is all not considered part of like database courses, okay, so we don't ever bring it up. But at some hardware low level, then somebody would have to worry about it. Okay, DBAs don't even know or care about this. This is actually system engineers, people that work for people like Oracle. They configure all this. Okay, so you can read about SANs. In the meanwhile, just to get back from that, we're just saying use RAIDs to provide like high speed like data access. And then the ultimate purpose of the whole performance tuning is disk contention, meaning you don't want to spin these disks any more than necessary because they can fail. So try to make an optimal access plan so that you don't have contention, you don't fight for this disk resource. And then, like I said, if something is used quite a lot, like your GPA column, then they can go in their own table space, they can go in some high-speed data disk access even. On the other hand, things like where your hometown is and what is your undergrad GPA can go in a tape robot. That's what this means. Yeah, so then that's literally what I just said. Storage volume is things like RAID, tape drive, SSD, solid state, RAM, all of those are separate volumes. And then you can store indexes and high-speed volumes because in the end, indexes should be used very fast, right? High speed. And then the actual row IDs, like next speed. So always keep indexes in high-speed memory. And then afterwards, as high speed as possible, the raw data. And it goes like that. Let's use data, not so much. All right, so one of you was asking about the access plan, what can I do? So this is a MySQL document, but the same idea applies to other systems as well. And it's highly readable. It's actually a lot of fun. So maybe after this course or, after the midterm or something, read it. I won't ask you like lots of detail from here, but it is neat. It's just a pretty good explanation for everything that I told you. To even have SQL examples. I'm going to scroll through it really fast, okay? So what is an index? There will be 3 index you can read about, then where they're actually used. This is what you would do, and this is how it's actually used. So primary key search again. One question was, are primary keys always indexed? Yes. So that's exactly why. Looking for 12, you can quickly find 12. And then so tables for the explain plan, that's really all you do. So when you say explain plan, that is when you actually see the so-called, compile version, which I've been calling compile version. And then this is what it looks like. So when you say, like right here. When you say select star from city one name equal to London, so select all the, basically select London, right? And it's gonna have like all of these, so what table is it gonna look for? What keys, and then what is the key length? How many rows? That's not a very cool access plan, but you can do many more though. Alter table. So then you make some change, and then you say, what is the access? Like, how do you actually make that change? Like, how did this alter table command actually occur? Did you put up something? And then index use combine. So combine indexes. So you can actually combine more than one index. And also, what if your query, has something where the columns that you're using, the column names in your query, has those columns indexed? Then you have something called a combined index. And so those can also be used to speed up your query. So there's lots that this goes into. You just read them, okay? Okay. So now the explain plan is getting bigger and bigger. Then covered index. Yeah. Okay. This fields in the index. This is also very interesting. See here, what they're saying is, suppose you want to search by, like how much money people make, and you also want to search by state. It depends on which one you want to do first. Like, is the query always like, give me all the highest paid people in California? In which case, California should come first, and you can do it. Or the other way around. Give me throughout the US, people that make like 10,000 to 15,000K. Then this order would swap. Then that will be the higher node because you can easily first search on those, and then only for those go and search for like state names. So it's one or the other like that, okay? So whether you do this or this depends on the usage case, that's all. So in the meanwhile, CG said all kinds of things. Software-based RAID. Wow. Well, you're pretty advanced. You have your own file server. I like that. Okay. I'll put it up and bring it up. Thank you. Yeah, they just tell you, okay, so read it, okay? And then group by. So what happens when you actually do things like group by? Then group by is actually served by something called a covered index. Yeah, so this is way more than what I want to spend time on, but it's fascinating. If you like all of these, you can do it. And the same access plan command, you can do it in Oracle, but you will get a very different looking result, but it's doing the same thing. Cool. See here, they actually have like an index, okay? Because somebody made an index for that. All right, so this is like a neat document for people that like to get more into indexing. Wow. Yeah. We're 20 minutes behind. It's okay. Can the DB? Yeah, right. It actually can, believe it or not. Oh, yeah, right. So based on usage, right, this is where machine learning, so-called machine learning comes in. So gradually what is happening is so many of what I told you is almost done automatically. So yes, over time, suppose a system watches of these two possibilities. Do people search for salary first versus states first? So say all of last year, 10,000 queries use salary first, 100 queries use state first. The system automatically will switch to an index where the salary is at the top, believe it or not. It is learning from people's own queries and it gets smarter and smarter. So that is highly possible. Just basically throw more computative meaning. I would just basically say machine learning. I mean, it's all machine learning, and I cannot wait to tell you. I'm just fascinated by the whole field of machine learning. I'll tell you a hell of a lot if you wait, but loosely machine learning, which is just a fancy term for saying I'll just look at the data and then find the pattern in it and modify myself. Easy. Okay, guess what? We will actually keep going because I want to keep going. I want to tell you about BI, okay? And we will take a break when the time comes for a break. BI is the next big, small at the same time topic. It's an easy topic. What we used to call BI has now a new name. It is actually called data science. So when you talk about data mining, data science, it is simply a fancier way of saying business intelligence. It's not that business intelligence went away, but what I'm saying is historically, what we today might easily call data science, data mining, used to be called by a different name, BI, business intelligence. So I'm saying to you that this is where the origin for things like data science came from. So it is actually super good to know what it used to mean. Okay, so BI. I'm going to tell you a lot about BI, 30 slides worth, and it's also cool. The bottom line is just simply this. I won't even click on one slide. I'll just talk for a little bit, okay? What is happening is with BI, you have just one goal. There are two words in BI, remember, business and intelligence. Business might mean someone like Ralph's, or the Shell Oil Company, or the USC Keck Hospital. It's a business after all. Everybody is a business. Even USC is a business. So that's the business part of it. Intelligence is not machine learning AI. It just simply means like, what can you tell me? Like, what can I learn? It's called, like in the spy community, they would call it intelligence, classification. So then the word, what they mean by the word intelligence is, what did they learn? Like, what can I learn? We use the word intelligence, okay? It is not about AI. So then what this means is, what can I learn about my business? Like, what more can I learn about my business than what I already know? Obviously, the CEO, the managers know a lot about Ralph's. They're constantly modifying products. They're ordering new things. They're stopping ordering new things. They're changing the layout of the store. They're printing new coupons. They're putting out new ads. They're doing all sorts of things, right? Changing the logo, anything they, like do more business. But on top of all of that, can I somehow find out even more so that I can make even more money and make my operation even more efficient? Then we call such processes, such tools, such databases, BI. So BI is ultimately a set of, again, tools, meaning there's some software you can write. SQL has been augmented by exactly 2 new keywords, okay? See, it's all the SQL that you already know you can use for BI. But then there are 2 new words. One of them is called cube. The other one is called rollup, which are all in the very back of your 30 slides here. So everything that I tell you is coming up. So when I say tools, all I mean is, some SQL version that will let you run these cube rollup commands, but also databases. So what kind of database do you need for doing BI? It's really the big one. And I'll tell you the answer. It is a kind of database called a data warehouse. It's a warehouse. When you think of the word warehouse, a warehouse store, you quickly think of a place like Costco or Walmart. You walk into Costco with your huge, massive shopping cart. It just makes your head spin for a little bit, right? These things are huge. Like, oh my God, that is like half a mile away, okay? This big box, okay, with filled with stuff that you probably don't want. I usually go to Ralph's and buy, a roll of like 12 rolls of toilet paper, I guess, right? Just like one pack. Here, it's like 100 roll of toilet paper, okay? Everything comes in like large quantities. So that's exactly what a warehouse is, a warehouse store in this case. So the word warehouse automatically just means piling up of something, just pile it up. Why buy just a pack of 6 bottles? I'll buy like 64 bottles. Oh my God. And obviously it's cheaper if you do that. But still, why the hell are you going to store it? In your garage. Then where will you store your car? On the street. Duh. So people do all these crazy things. In any case, data warehouse is exactly what you think it is. You pile up data like hell. Just a huge database. Fill it with massive amounts of data. Just fill it. Then you get a data warehouse. And then all the SQL that you run and all the magical results that you get out of it is called BI, business intelligence. Then the next question is, where is all this coming from? Like, what do you mean fill the data warehouse with data? Well, it's coming from, so California roughly looks like that. Los Angeles, Santa Barbara, San Diego, San Francisco, Sonoma County, every single Ralph's in California. They've been running for years and years and years. And you have every single sales receipt from every single Ralph's that ever sold anything to anybody. So one of these receipts belongs to Sati with my club card. Then a few weeks later, again, me. They have all the data, sales receipt data. They can take it all, just pile it right here. And then they can ask one question. How are we doing on the sale of plastic water bottles? There's so much environmental, consciousness these days, and so people want to, do the right thing. So should we stop, stocking too much plastic water bottles? Should we slowly phase it out? It's just a simple question. This can answer you, okay? What cannot answer you is just one person's bill. Like, I never buy water bottles. So I would be a bad data point, to decide yes or no, okay? I'd completely mislead you one way or the other. But if you connect the dots to all of them, you get magic answers, right? Yeah, you can call it many, many names, right? Yeah, absolutely. It is a normal query, but it's a query on like massive amounts of data. That's all BI is. Sure. Okay, so over time, since 1985 to 2021, water bottle sales in like hundreds of thousands, okay, per week. Just plot all that from here. It is doing this, okay, like this. And then through the 90s, people got very lazy and highly convenient. They want a lot of water bottles. And there was a brief, and then people started saying, oh my God, the earth is burning, throw plastics out. And then now it's doing this. Then the CEO should say, at this rate, we'll just be stuck with massive water bottles in like 5 years. Stop it. Just stop selling today. Phase it out. That is exactly what it is, okay? So what is the difference between a warehouse and a database? The way the tables are stored, okay? So normal database, this normal table rather, you can store like lots and lots of highly like unnormalized data just for fast reasons. But here what we can do in a data warehouse, you can actually normalize it, but not randomly normalize it. You can normalize as a tree actually. You can do a tree of tables. So I'm going to show you like lots of slides, but imagine a tree of tables, and what is causing the hierarchy is like normalizations, okay? You're doing increasing levels of normalization. That is what can be stored in a database. So it is all still relational database, still SQL, still primary keys, still foreign keys. But now your tables have a very interesting structure. A structure that I actually named. In fact, it is called a snowflake schema. What I just named is actually called a snowflake schema. It is simply ways to organize tables, okay? Yes. So then the reason to do all this cool stuff is then when the analyst says, well, fine, I'm not going to throw away water bottles, probably this fake data. Just tell me what I should do for, like, Los Angeles and all these stores. We'll do separate decisions. Then the analyst can actually go and do that and pull only for Los Angeles. So imagine LA's water bottle usage went up like that, right? Well, like basically La La Land, right? We just don't care about anything. Who the hell cares about the earth? I want my water bottle. So our trend just never stopped. So in LA, it would be crazy if you stopped selling water bottles because then your customer would go to Vons, okay? You probably should stock more water bottles. So now I can actually drill down in the data and see what is happening, not across the whole Ralph's. I can do it city by city. I can do it region by region. I can even do it zip code by zip code. All that magic is possible because you pre-took your data, you broke it down in every possible combination, and so easily at runtime have my dashboard update. So I'll just walk to a dashboard and touch, and this will update. The graph's gonna update. So that is the idea of what I'm gonna tell you. Cool, right? Like this. So in the end, all the data analysis will show up literally like in a car dashboard. You can have multiple meters, dials, bar charts, line charts, all of them. If you set it up so it be, you can animate almost in real time. Jeff Bezos, every single minute, you look up his wall, there probably is a massive display that shows how many more millions or billions has he made every single day. Okay, this is literally that. If the dial goes to yellow, somebody's going to start panicking, like whatever this dial is. If it goes in red, they'll start like texting people and calling people. So these can take massive amounts of data and so easily make it digestible. Just one glance is all I have to do. Okay, like how you all set it up. So the whole SQL that you learn, data science, machine learning, is all to service this. In other words, your end goal is how realistic is this? Meaning, how fast can I do it? And how useful is it? Like, what does the boss want? What does the company want? We'll find a way to make it happen. So that is the reason to do data engineers, data scientists. Everything is. So Salesforce is a company that specializes in creating these dashboards. Particularly, they started with the UI, but now they can do some analysis as well. But one way or the other, all the things I'm going to tell you will actually end up there. Okay. So now you got the big picture. The rest is actually very easy. The actual technical things are the roll up and the cube idea, and also the snowflake and the star schema, this thing called star schema. So the BI is manipulating data. Sure. So the BI is simply just a bunch of queries ultimately. And yeah, the DB is storing the data. And we call the DB DW. We call it data warehouse. Cool. Okay. So now all this is going to become so clear. Okay. So BI is just simply a comprehensive, cohesive, integrated set of tools and processes. You capture, collect, integrate, store, analyze. Too many words. Okay. But all that means is this capture is not what happens at a Ralph's checkout. That's already happening anyway. But then when this warehouse has to be built for the first time and then gradually updated, that's what this capture means. This means I'm bringing from all the stores, the receipts. Capture, collect loosely mean the same thing actually. Integrate is where it can be a little bit different. If you're Ralph's, all your sales receipts only show dollar figures, okay? But supposing you're Aldi. Aldi is a German-based, like a grocery store. They exist in many countries in the world. So Aldi says, wow, how are we doing all over the world? And gradually they'll then go to continents in other countries, what. But then they cannot just add dollars and euros and Singapore dollars and yens and RMBs together, okay? It's going to be meaningless. So the integration might consist of some transformation. They convert all of them to US dollars, okay, for example. Or you cannot do date range, storing by having US based, month and then date first, foreign, all over the world, date first followed by month versus US month followed by date. See, then you'll get completely different results. The January 5th is not the same as May 1st. So you need to find one common storage. Probably because they're in Europe, they'll pick day followed by month followed by year. So all the US dates would have to be flipped. That is all called integration, okay? So integration it might involve some data processing just to bring it all to a common format. Then storing is where the whole Snowflake store, all that comes in. And then this is where the actual queries run. So this makes a lot of sense. Okay, why do you want to do it? Because you want to support business decision making. That's where the intelligence comes in. You're gathering intelligence to give to the board of directors and the management. It allows the business to transform. This all like standard stuff. Okay, you have a pyramid. You take raw data, all your sales receipts, one at a time, piles and piles of sales receipts, and then they become information that are structured and stored in a database. And then you extract some value out of it. We should be stored. Ralph's actually did this, right? Over time, the last maybe 10 years, I'm going to say, there's been an explosion in the vegan population, meaning people are drinking less cow's milk and more soy milk, cashew milk, almond milk. So I've seen it at Ralph's myself. So there's more and more space that is used to store chocolate almond milk as opposed to chocolate cow's milk. So that is the decision that they're talking about. Like, why would I have to do something? Justify the reason. Well, because people are buying more and more of this and less of that. So you do it. BI is meant, how do companies compute? Yeah, I mean, many ways. It's what I told you, okay? So to that, it's based on how fast you can gather the data. You don't have to do it in real time. If you do it in real time, that is called streaming. So there are streaming versions of all of these, streaming BI, okay? Then you can do it literally every time somebody buys something. Some tiny dial can actually go up somewhere, but that might be too much, okay? But that's probably what Amazon does. Others are not that fortunate to, have that much computation. Then you can do it like one time per minute, okay? So you can actually do streaming like this. It's Power BI. That's a special, that's the name of a vendor. So if you buy Power BI, you can actually do data streaming through Azure. So your data would end up on the cloud, and then from there be streamed to Power BI, and then these dials can just change like literally, every second even. Twitter would have exactly this, about tweets. They analyze tweets in real time. So real-time BI is a whole world all unto itself, but not everybody needs real-time BI, okay? Okay, so there's a lot that you can just read on your own. All right. So then in the end, you want knowledge. You want to do something useful with all that data that you collected. All right, so then the thing could not be simpler. So what is all like part of BI? On the one hand, people are involved, like business analysts and managers, they're all the people who want to do BI. And then you have these processes, such as, what kind of ETL, this extract, transform, load, like what kind of data transformations would you do? Or what kind of SQL query are you going to run? Or what kind of analysis are you going to do? They're called processes. Management is an upper layer that says, I want to make sure that this is all done properly. In other words, how often would you update a data warehouse? I told you, real time is a luxury for a lot of people, but would you do it every week? Would you do it every 6 months? So a management layer has to decide all of that. So management is involved. And governance says, what should we do with all this data? Like, should we store it forever? Does the government does it say to you, I need to store this data for 8 years? It's like business compliance. So all that is a layer called governance, like doing it legally correctly. Can I just go and modify some data warehouse when nobody's looking? Because then my results will look great. That is basically illegal, right? You're completely lying, because the data warehouse should absolutely be not touched at all. Once your data goes in the warehouse, it should be pretty much read-only, because this is all by definition past historic data. This is coming from things that already happened. So if you change something in here, it means you're lying about what happened. Okay? Yeah. So then that's like a read-only database. Anyway, so there can be policies and fines for all of that. That is called governance. So there's a whole bunch of things that go with business intelligence. Okay, so why would you do it? I told you all the answers. The biggest reason is you want to do like more, informed way to make decisions. And then it can also serve as a way to take databases from many different parts of your company in many different parts of the world who normally don't communicate with each other. Even though it is one company, it is a multinational company, but each country has its own culture. They all do their own thing, and they don't even talk across each other. Then at the very top levels of the management, they would say, this is unacceptable. We need all data in one place. But they're not cooperating. What can we do? Well, pretend that you're making a warehouse and ask for it. Then they'll give it to you. So that's this reason, okay? You're trying to be like one common architecture, and you basically trick people into giving you data. These are real world things, by the way, that actually happen. And then you can have one UI for everything. You can have one, again, this is ultimately what it is. So there's no I don't know what shit I don't know what hated. There's only one single truth. It's all in one place. And then in the end, maybe it makes everybody cooperate and work better. That's all it is. Okay. So then this is all like historically fascinating. The notion of analyzing data goes right back to the 1960s, really. And then IBM, these are like line printers. So there'd be a little, there's holes here. And then there's like one long sheet of paper is folded like this zigzag fold. And then there's a dot matrix ribbon that actually goes, let me show it to you. The dot matrix printer, say line printer, say line, just say that. Okay, I'm gonna say dot matrix printout, just to show you what it looks like. Yeah, very old-fashioned. Yeah, like that. So this is what I'm trying to show you, okay? So these days, nobody ever does all this because you have laser printers. But there's a roller that actually pushes the paper up. The paper automatically folds beautifully. So this is how business reports used to be done. So now you can do it for it. I actually have a program in Python that does it. So you can, but you can do like Mandelbrot fractal there. This is what it used to look like. So old, but it's data. Look at it, it's actual data. So IBM mainframes ran the old-fashioned business reports at the time. And look at all this, all about call numbers, some aggregation number. They took out the name. It's about money, right? Borrower's name, right? So it's all about money. Okay, so when the loan is due, I guess. Therefore, that's where it came from. Centralized reporting, because there was an IBM mainframe that had all the data, and you ran some Fortran or some COBOL program, and the COBOL program produced this report. Then along came the 80s, personal computers. So now you have, Bill Gates, selling Windows, and you have Apple, Mac, what. Then now the small businesses can buy Excel spreadsheets and then use Visual Basic to plot these and then put them in PowerPoint and then do their own BI. Just limited, just the one company. You hire somebody to write Visual Basic macros. People still do this, by the way. You can do Excel macros, but that's a limited, like just one company at a time analysis, but still analysis. And that's all the company wanted. I'm running some kind of an arts and crafts business. How much money did I make last year? Do that. The things that I asked you, by the way, for your homework is a lot like all of this, actually. Honestly, I didn't tell you that. Now that the homework is over, I can actually tell you there are companies who actually sell exactly the kind of software that I asked you to write. And then that means you can go and work for these companies. Dental dashboard. Business dashboard. Yeah. What I asked you to write is real. Except you can buy all this software. Your Jarvis Dental Analytics. Oh my God. So KPI stands for Key Performance Indicator. It's a common term that we use. Okay, KPI, Key Performance Indicator. That means some number that you're looking at, like how many visits of patients per day, or what is the average money we made per day, or what is the average room occupancy percentage. I have 8 rooms. How many rooms do we use on average? All of that, this Jarvis company can actually plot for you. You meaning a dental business owner. Look at all this. So underneath, they're probably running SQL. I asked you to write that. Oh my God. All right. So then it's cool, right? There's many more of them, Blue Notes, and on. But that's exactly what they do. They specialize in dentistry. They know all the different operations, procedures. It's all in the databases. And then they hook their stuff up to insurance companies. They make it so easy for a dentist to run like a business. That's all it is. It's a business-specific database. All right, so we've veered away, but that is where the data, the dashboard comes in, okay? In diagnosis, where you can say, like, who is the dental hygienist that is not being very useful? Like, who is the least used person in our company? We'll have to start giving him or her more patients. That's all called diagnosis, okay? Like, fix problems. And that's all it is. Cool. Okay, so then that can happen in, on a PC, basically. But then along comes the 90s and the 2000s and 2010s. This is when the internet came along. So now all of a sudden things got bigger in terms of how much volume of data can you handle. And then the internet is like 93. So then the 2000s, early 2000s came along. Things like Salesforce got massively large. Salesforce is one of the highest, like biggest, most valuable companies in the US, actually. You can look it up. Mark Binoff is the CEO. Then they got so huge because eBay, LinkedIn, they all said, wow, we want Salesforce. And so then that's what that is. Now the dashboards, all these, this was numbers, by the way, no graphics even. This is very limited, simple, boring graphics. Now you have graphics that are actually animating and also interactive. Somebody could go and tap a little button and then the analysis can go one level deeper. Like, don't show me all of California, show me only Southern California. You could not do that here, by the way. Someone had to modify the Visual Basic code and the business owner is not going to do it. Here, there's some COBOL program, so there's no data even at that level available. They only collected data for a whole state. So everything got better in the 2000s. You have more data, more analysis, more interactivity. And then after that, you can now do it on your phone because it's all done on the cloud anyway. The cloud just sends you a picture. So from an airplane, 30,000 feet up, the CEO can start tapping all this. And then some cloud runs some computation, and then the CEO gets the results back. So before they land, they can actually prepare for some meeting where they need all this data. But it's just wildly cool, okay? So I used to work for Autodesk. So then so my boss was basically only 2 levels below the actual CEO of Autodesk, okay? So in a way, you can say that I was only 3 levels down, although I never thought of myself that way. So he was pretty high up, and I worked for him. This is what would happen. So I would be sitting with my coworkers in Venice Beach, right, so eating lunch somewhere. All of a sudden, my phone just goes off. And then it's Brian. So Brian is my boss on the phone. Sati, where the hell are you? Having lunch, Brian. What's up? Get the fuck back to the office now. Brian, what happened? The guy is almost popping a vein, right? Because his boss called him and then asked something about like Maya software and DreamWorks or something, right? So then what the CEO or what Brian did was literally look at these numbers in real time. In other words, this is what managers do. They just stare at these numbers. When the numbers go in red, they just basically panic, okay, and start yelling at other people. So then I drop my lunch, literally shove, just wolf down what I have and just run back to my office and put out the fire. So that is all like a real-time running of your business, because that is what the indicators can tell you. It's just crazy cool, like how far we've come. I don't know what's beyond this, by the way. You already have so much of what you want. Then the notion of doing BI like that, someone staring at a dial and going crazy, is all possible because of good data, good tools. So effective BI depends on the quality of data. So you need to be very careful when you build your data warehouse, but that's not what this is. Sorry. Yeah, so when you build your warehouse, it's operational warehouse, you need to, sorry, I will tell you better things, okay? Yeah, I'll just back up. Okay, so this is really where the whole data starts being gathered. In other words, this is your individual sales receipt. There's two kinds of data, okay? There's basically collected data and then individual data. So you can call them transactional data versus aggregated data. So transactional data is all your individual pieces, one sales receipt at a time. Right? Okay, so this is what I'm saying. You have every single sales receipt. Even there, if you want to do analysis, even at that level, when you store all the data, what somebody bought, don't just store just the items that they bought. If you can do any grouping, like this is groceries, this is also groceries, this is stationery, this is dairy, this is, I don't know, something else, hardware. So also have that extra tag so that when you collect them all, you can do extra analysis. Then somebody can say, how much business did we do on like hardware? Then you have the data available. So everything starts at that transactional operational level, okay? That is the lowest level of data. So, and then you aggregate all of them and then build the warehouse. And so then if you do this extraction part correctly, you'll have good data here as well. So we just talked about two different levels of data. This is like the big picture, historically looking backwards. And this is the little piece one at a time that gave us this big picture. And then you're trying to extrapolate the future from there. So now you understand? All right, so operational data. Operational data is not useful for decision support. So decision support is this. In other words, I cannot look at just one receipt from somebody or even 1,000 receipts and then decide the fate of the company. Like we should close our Europe division because Europe is not doing well. You cannot possibly tell that from here, right? Because you need like way more. It is all about looking at the past. So time goes this way, then you are here by definition, this right now. Nobody knows about the future. But if you look at some trend that happened in your life, because some trend, you can literally connect the dots and say, wow, if nothing else changes, I think I can safely predict that I'll be over here. This is all we're doing, looking backwards so that you can look forwards. Okay, so therefore just one receipt will not do. I need like a whole collection of them. That's all I was saying. So then you're storing in operational data. It is stored in standard relational databases, okay? So then that is done to store transactions. In other words, every sales receipt is what you call operational data because they're one by one transaction. And then there's a lot of writing. You're just constantly writing. You're hardly reading this because there's no need. On the other hand, in here, decision support data. By the way, this should probably say operational data, okay? Meaning day by day, one receipt at a time. This is the aggregate, this is the warehouse. So it's different from that because it is a whole time span. It spans the last 50 years, maybe Walmart. Granularity, again, it tells you, like I told you, for a sales receipt, not just every item that somebody bought, but also what kind of a category is it? What subcategory is it? I can store so much. If you buy one t-shirt at Amazon, they just go crazy like with all the things that they store. What kind of material is it? What color? What vendor? Is it long sleeve, short sleeve? And then, in what country was it made? They can do like so much, but that's not really granularity. That is just simply so many tags. Granularity might mean, where did the single order come from? Well, it came from North America. It also came from the western part of North America. It came from California. It came from Los Angeles. It came from La Cosena. It came from this block of street probably. They can store all of that simultaneously for the one t-shirt that I bought from my house. That's what they can do. Then when they analyze, the analysts can say, how do we do on t-shirts in northern Los Angeles? Then they'll go to my zip code. They'll find out. So that is called drilling down. It means you're going to lower and lower and lower level of detail and doing micro analysis. That's what this is. The opposite of that is roll up. Then Jeff Bezos gets pretty impatient and says, who the hell cares what Steve's doing? Just tell me the whole world and how are you doing black t-shirts? Then you go the opposite. Then you can go the entire world and say, for the whole world, what does black t-shirt sale look like? Because they have that data. Okay. There is notion of granularity. Second, fine grain. Fine grain means this. Rough grain means that. Drill down like a drill bit, just drill, 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 go down. Roll up means like a blanket, just roll it up, roll it up, roll it up, go higher. Then you have the 30,000 feet airplane view. This is like a pretty deep view. Zoom in, zoom out. That's what this is. Okay. Then I'm going to tell you how we actually store tables to do that. All right. So therefore, again, this exact slide is now in the form of a table. So what are these differences? We keep talking about. The differences are very simple. You can measure like how these differ in terms of all these parameters. So you take data currency, meaning how update is my data, how up to date is my data. And the idea would be in operational data, by definition, suppose somebody was at Ralph's last 5 seconds ago. When they walked out, we have the data. So it's highly current. On the other hand, decision support, unless you do streaming version of this, would not be current at all. It is only as recent as the last time it was updated. Maybe it was last week. So you cannot ask for anything more recent than last week, okay? So it is, a little bit slower, older than this. This will always be current. What about this? Again, granularity. So this one, the sales receipt simply stores like exactly what somebody bought, black t-shirt. But then when you put it into this, you can then find out, like I told you, where my order came from, and simultaneously enter the black t-shirt into all these North America, city, zip code, whatever. Then that way I get summarized data. It's the same data, but now I have many versions of it, so to speak, like in many different tables. Each table is at a different level of aggregation, meaning some show me continent level, some show me like region level, some show me state level, city level. Then that is the notion of summarization. In other words, this exists at multiple levels of granularity. This only exists at one level, the bottommost level possible. Somebody just bought something. Okay, that's all it is, okay? So then summarization is pretty low because you're not summarizing anything. Here you summarize, meaning you put it at as many levels as possible, and on, okay? All right, so this is the main thing, maybe this is the most useful. In here, we just don't care. It's simply just a, point of sale terminal database. POS, not the POS that you're thinking of, the other POS. So POS terminal, Urban Dictionary POS. Okay, so the POS terminal is the point of sale terminal. That's what I mean. Go ching ching, you simply ring it up. So then those things are what store the data in a standard relational database. But on the other hand, a data warehouse stores data in a slightly different model, complex structures, what we call star schema, snowflake schema. That could be relational, but you can use other non-relational databases also. You can do basically like a C++ version of multidimensional memory. In C++, all the memory is only linear because you've got a pointer to a block of data. But you can have many of those pointers, pointer A, pointer B, pointer C, pointer C. But I can have a pointer to those pointers. Now I have a second level star star. Now I have a two-dimensional array. And then I can have a bunch of these stars. I can have a star that is going to point to stars. Now I have a three-dimensional memory. You can build such databases yourself. Just crazy cool. Then you ignore Oracle, ignore SQL, just ignore everything and do everything in C++. And it'll be super fast. And some people do it like that. They sell you entire warehouses where it's built on multidimensional databases. Okay, so you can do that. And then in a transaction type, so what happens, when somebody buys something, you're updating the database. You're just writing. What happens when you do decision support? You're obviously reading and reading. So very different, extremely different. Here, writing should almost be illegal, okay? And here you can read if you want, but there's no point in reading that. And then transaction volume, again, high update, it's constantly being updated. And here, this is not growing at all, but all of a sudden it'll grow like crazy when you load like a ton of data onto it. On and on, okay? And here you have to be able to write. Here you should be able to read. Query activity. Nobody queries these point of sale terminals. Useless. You query it all the time. That's the whole reason to do it. And then what can you query if you can even query? Like almost nothing. Here you can query almost everything. And then what query can you possibly run on my sales receipt? Not too much. All of BI. How much space do you need? Not too much. Massive. So, right, it's a very different kind of data. That's all it is. And it's useful. Supremely useful. Now you know a lot about BI. Cool. So then, therefore, what must the database schema do? Like speaking of, like how should you store warehouse data? You should be able to store complex, non-normalized. So not everything is normalized, but there's a hierarchy, I'll tell you. And then the data must be aggregated and summarized. This is where the whole hierarchy comes in. I need to store the same fact. The real low level, the receipt is called a fact. Every receipt, every sales receipt is called a fact. So if I compile in my warehouse, just only the facts, I have this massive table with everybody's sales receipts all below each other. It's useful but not super useful. We call it a fact table, okay? So in a fact table, this is a warehouse again. It's a data warehouse. I make one table, this is starting table called a fact table. In the fact table, I take every single sales receipt for every single person, all the billions of people that have shopped with us over the last 20 years. Each salesperson, one receipt, the club card ID. So then what the heck is this? It's basically all sorts of things. Timestamp, like when did that particular receipt occur? And then, what is the customer's name, phone number, whatever. But here is the main thing. Every single thing that Ralph's ever sells is a column. We have a product ID and a quantity. So then say I bought milk today, 2 gallons of milk. I also bought, deodorant, just one little thing of deodorant, and on and on. So that is what is in that single sales receipt. They can store that in the fact table. So the fact table is pretty low level, but it stores everything for everybody. Then you can use it as a starting point and build even more and more aggregated tables, which you will actually use for querying. You can query here also, but it's going to be very slow to look for all the things that you want. But like almost indexing, you can pre-calculate and make newer tables that all contain the same data, but in different versions, okay? But then now you can do BI on this. So that's the idea. So it needs like those specialized tables at the bottom. Hey, cool. Okay. And then so queries, it's all about slices. I'll show you a picture soon, and then you'll know about slices, okay? That's what I mean by a slice, like right here. All that this means is, say this is time of day, morning, afternoon, evening. Say this is location, west side, and then midtown, East LA. And then say this third dimension, this dimension that goes across like that, is product category, groceries, dairy, stationery. A slice just simply means give me any two, but then for a certain value that I specify. Like for example, say this is time of day, I told you morning, afternoon, evening. So for afternoon, for like all of LA, tell me like what we sold. Then that pink slice that you extract is only for the time frame, but it doesn't matter what product, doesn't matter where. Then that is called a slice. You extract a slice by cutting off just one dimension, okay? So in one dimension, you make a slice of the dimension. I don't need to know about morning, afternoon, evening, only afternoon. Likewise, the top slice would be only evening. The bottom slice would be only morning. If you slice it like this, if you slice it like this I told you is location, store A, store B, store C. This middle slice would be only store B. There's something bad about store B. People are complaining. What is going on with the sales? Can you tell me? Slice it there. So once you slice it in 2D, you can slice it again. Then you call it dicing. So once I know about what happens in the afternoon, you can say what happens in the afternoon at that store. Cut it one more time. And I get little cubes right there, right? That is called slicing and dicing, okay? It's what all this is. So a data warehouse can be sliced and diced. Here is only 3D, but you can do it for 100 dimensions. Just slice off one dimension at a time and keep going. Slice, slice, slice. All right. So that is what this is. So queries must be able to extract multi-dimensional slice, not just time slices, any slice really. Product slice, employee number slice. You can even store all this data based on who was at all these point of sale terminals, and then why are all the customers avoiding this employee? Why is her output so low? And then you basically secretly watch her or him, and then they yell at people. They rude to customers. They throw their bags in the cart. So then you have to discipline them. You can find that out because you actually have the data. It's crazy, what you can do with that. All right, so then it's all this. How do you extract? How do you load? Batch and schedule data extraction, and then support different data sources. Yeah, this is what I meant. So when you're trying to get receipts from all over the world for your business, you need to even look for inconsistent data, or maybe data validation. Like how do you transform? What should we keep everything in euros, for example, or should we throw away anything that is less than like $100? It's not worth saving. So all those decisions you're supposed to make. So then the processes would support like all of this. Those processes together that ingest, it's called data ingesting, okay? You ingest the data. You have your warehouse, like I'm talking about this. You have so much receipts that are coming in. You need one massive process, first of all, to build this. That massive process, that ingesting process is called ETL. Your data ingest, you're eating data, literally ingest data, incoming data. Extract, transform, load. Extract means from each sales receipt, get only the pieces that I want. I don't need, I'm not looking for water today. So then in the extraction, don't look at, just delete the water that I bought. That is called extraction. Transforming is when you would make the same common date format or the same common currency format, or any other transformation, okay? Or maybe convert all the names to uppercase, I don't know. That is all called transform. Load is when you would literally make rows of data loading. So extract, transform, load, okay, ETL. There are many companies that just only do ETL for a living, meaning they go to Walmart, they go to Bank of America, and then they ask them, give us all your data. We'll sign an NDA, we'll do ETL for you. Then the ETL warehouse building companies. These jobs are very fascinating. ETL developer. And they pay you like crazy, by the way. Okay, so ETL, just show you ETL jobs. Okay, show you one. Like, what does a typical job look like? Okay, so it's not bad. ETL report developer. They ask you for things like SQL, all the things that you know. Urgently hiring job types, like right there, T-SQL immediate. T stands for transaction SQL. That's the same thing. ETL developer, ETL developer, and then all this, analysis, vision plans. You get all this stuff, like right there. Stored procedures, functions, triggers, complex, just over and over and over the same thing. Just you can look at thousands of them. Okay, they're all the same. Just crazy cool. So because it's so important, yes, extract, transform, and load. I have slides for all these. I just verbally mentioned them to you, okay? There's the word SQL right there, there's the word SQL right there. Okay, point made, okay? And so you need to know the whole Snowflake schema, which I'll tell you. Although in this case, the word Snowflake is actually the name of a product, okay? But they named the product Snowflake because there's a database, like a table format called Snowflake. I don't know if the two are related. All right, so one last time, Microsoft wants ETL, why not? Okay. Informatica is one other piece of software that actually does ETL. So here they want you to know Informatica. So once again, write the entity models and all the same thing again. Yep, over and over. See, they want modeling experience. Apply all these. Cool. So you can go in, get into the industry of being like an ETL person initially, and then move on to actual data science if you want. All right, so that is what this is, the ETL, like right there, this part. And then you should, so what kind of a warehouse, hardware should you have? You should have like massively large tables, sizes and so forth. That's like VLDPs. Okay, so these things are just simply for any database. You need like a very big database basically, and you can obviously know why. I want to move on and show you other things though. I want to tell you. Yeah, so this is again something we've seen. The same slide we saw before, like here, is summarized one more time. What is the difference between day-to-day operational receipt data versus all-together decision support data? What are some differences? Here they are one more time. In the operational receipt data, the integration is not too much integration, whereas in data warehouse, it is all unified, highly integrated. And then subject-oriented. So that just means in the operational database, you don't know about subject. Subjects just simply mean, what did you buy? Did you buy from Amazon today, electronics, or did you buy, I don't know, toys or something, or did you buy clothing? All of that is called subject-oriented. In here, it's hard to tell subject orientation because the receipt is just a receipt. But then now a process can analyze with one receipt and then know I bought a t-shirt, therefore it must go in the clothing category. So they can make it subject-oriented. Then they can store all the subjects even differently if they want. So more analysis here. And then time variant. I told you, in a transaction, you just simply, the sales receipt has exactly the timestamp. So, date, hour, time, second, right there. But then here, it's all historic, meaning you can go back last week, last year, last month, last 10 years. So you had time dimension. And then non-volatile. So this one is not non-volatile. It is volatile in the sense that the database is being written all the time. And then this is the big deal. It should be non-volatile. Like you burn data into a warehouse. And then if you're changing it, it means you're secretly trying to cheat so that the results look good. In other words, the curve for the sales went this way. Boss is going to be mad. So you fake sales data so that the curve goes this way instead. It's horribly bad for all kinds of reasons, but that's what this is. You should not change this data. You should not have a legal need to change this data because this data came from here. So this is the past, so you cannot change the past unless, like I said, you can get away with it. So data is only added periodically. Once the data is stored, no changes. They say that over and over, okay? Because obviously, by the way, if you do business with the government, and then you have warehouse related to, those kinds of businesses. If you cheat and you make some fake report for the government, you can be jailed, so it might even be some kind of, offense that's punishable by law, jail time, or massive fines, your business is going to shut down. Even if all that is not true, you don't fake data because it is faking data. Then why even bother doing all this? Just make up a warehouse with anything you want, just make up any answer. Garbage in, garbage out, okay, so we don't do that. All right, so the ETL that I promised is here. It's a very simple idea. Just take all the operational sales receipts from like so many different stores and then extract what you want from them. And then transformation, I gave you some examples, but here they all are. You can filter, meaning when you store, you can even make like different warehouses. And then just based on what you're filtering, in other words, send all the clothing purchases here, send all the electronics purchases here. You don't even have to have one warehouse, by the way. When you make mini warehouses, like subject specific pieces of warehouses, those warehouses are not called warehouses. They're called data marts. Data mart, M-A-R-T, data mart. A data mart is the idea that a big warehouse is basically useless for everybody because it has too much. No product manager would actually say, show me the whole warehouse. And then how did we do last year? Only public Jeff Bezos cares, right? But instead, what most product managers at Amazon would care is, give me a warehouse for just my stuff, electronics. Give me a warehouse for just, I don't know, clothing, like I said. Give me a warehouse for travel, for cars, whatever in Amazon sells. That can be done by filtering. Every receipt, go here, go here, go here, go here. And I can build these so-called data marts. So data mart is a mini warehouse. Then different business groups would use different business data marts and then do the kind of analysis that they want to do. So you don't need to ever look at the whole thing. You can also go from here to here. You don't need to do it when filtering. Just put it all in one place and afterwards write SQL and then just build all these marts afterwards. So it's not that you have to do it when you're bringing it in, but you can do it during ETL. And then that is what yeah, exactly. So data mart is a filtered version, correct? Yeah. Wouldn't quite say it like that. I would say data mart is a subject specific version. Okay? It's a subject or topic specific version, which you can get by filtering. Because technically filtering happens at ETL. Okay, transform is the most obvious of all of them, right? That is when you change date formats, you change currency formats. Those are the two big ones. And then you can integrate. You can even combine things, okay? So there's like two different kinds of products you sell. In the warehouse, you don't need both those. Nobody ever tries to distinguish between them. You can combine them. That's integration. Aggregation is very similar to integration. So now you can actually summarize, integrate them, but at one level, at an even higher level. I can combine two aggregates and make an even bigger aggregate. So that's like hierarchies of them. And then I can classify them. So again, filtering and classification go together. This one like sorting almost, like one goes here, one goes there. Sorry that there are too many words that say the same thing. Just understand like what I'm saying to you, okay? Summarizing. While you bring it in, you can actually do a little bit of calculation and actually make a little bit of summary available. Then you wouldn't even have to run anything on here. You can directly bring in the summary. That's also possible. Not that commonly done, okay? So commonly you filter, which is classify really, and then you transform, and then you integrate / aggregate. So only three main things that you do. So after you do that, then you load, meaning you make your actual warehouse. So now this is all done, you don't need this anymore. Then the warehouse is highly integrated because it's all here. It can be subject oriented because you can get that out of here. It's time variant in the sense you can go back to any unit of time in the past. And then finally it's non-volatile. So now I have the warehouse and what do you do with it? So this is an older ad that I found, Informatica. It's also a company, by the way, Informatica. So then that's what they do. St. Louis, the one they call it this ETL Power Center. And see, it's like testing stuff. And then, yeah, the main thing is you need to know Informatica. Okay, so that has all of the processes in on tools that have SQL underneath. And so they just want you to run Informatica and then build like a warehouse for somebody else. So with this, you don't even need to write SQL because it actually comes with the product. Just learn Informatica. We get a free version and just learn it. Okay, so a data mart is what I told you. This is the one where you don't have like one big warehouse because maybe it's not useful, but you have mini warehouses. Mart. Ooh. There you go. So that's exactly what a data mart is. Mart. Okay. So then that is here. For small groups, obviously, just for like one unit, really, one business unit. And then why do you want to do it? Because it is lower cost, because it doesn't need too much disk space and you can do it faster. I have no idea what this means, okay? I don't know what this means. So ignore like all this. But it's an easier version of a warehouse because you don't need the whole thing. That's all. Okay. These are not rules, first of all. So, when you say rule, just mean like a checklist. So how would you make like a checklist of 6 things? In other words, what makes for a good warehouse? The warehouse and the operation are completely separated. So the ETL is a very clear process, okay? So these things, these sales receipts, don't live in the same database as the overall warehouse. There's no pollution ever possible. After you do the warehouse construction, just delete all this, just disconnect it. So that is a good separation to have. That way there's no doubt as to like what is actually happening. In other words, in real time, suppose it's changing. There's no like possibility that this is going to start changing. Unless you set it up that way, then it's streaming data. Otherwise, keep them separate. That's useful. And then data warehouse is integrated. I need to be able to query like all kinds of things. You've summarized it properly for me. That's true. It should contain historic data over a long time. This is also true. This is the biggest reason to do it, because then you can connect the dots over even the last decade if you want. And say, look, over time, slowly we're going down. Every year we're losing 10% of customers. What do you think is going to happen to us? Why did nobody tell me? Because we never looked. Okay, it looks fine, but it's like a slow burn. You're slowly being boiled to death, and you don't realize it. So then why wait till it actually like goes to zero? Might as well like stop now. That is the notion of historic data. And so then it's a snapshot of data captured at any point. In other words, look, you get the historic data from all the snapshots. Okay, so at any one time, today you take all the sales receipts. You have that if you want, but then you can also get the historic perspective of that. And then subject oriented, this is the same as integrated. This just means I can go and query it based on, I can slice and dice it however I want. And then it's read only, and then batch updates once in a while, then no online updates. So these things we already said. Okay, nothing new there. Okay, so this is where the actual, the technical part of it starts. It's cool, and it's very easy. A so-called schema is just simply column names that show up in this thing that I called the fact table. So I'm going to draw the fact table again. In other words, in a fact table, like one person's sales receipt showed up and became part of the warehouse, right? So one sales receipt. So this is like my sales receipt. Yes, my club card number is here. But also there's so many other things about me, right? For example, maybe this is the timestamp. Like when did this particular purchase occur? The timestamp. What is the store ID that I go and buy all my stuff here in La Cocina? The store ID, it's La Cocina store ID. And then like what part of LA would you call this store? This what is even the zip code? Zip code, so like 91214. And then these are all the things that I bought on that particular purchase, things binary turn on and off. All that is here, okay? So these big column names on which I can query all this data. So then they become what is called part of a star schema. In other words, the fact table, this one fact table is in the middle. It is like a massive, let me see if somebody's going to name it for me, okay? Okay, so there's a certain table type that I named in the past when we talked about all this. So let's see if we can name it for me. But these things on the spokes of this little wheel, all these column names. In other words, this says zip code. This says time. This says store ID. This says product category. So what kind of table have you seen in the past where, in other words, these are the column names, the zip code, and then this one is store ID, this product category. What do you call that table? Well, they're all like primary keys. Primary key, primary key, primary key, primary key, primary key. A table made up of nothing but primary keys.
Enums?
It's a bridge, right? It's a bridge table, remember? It's a bridge. I give you the usual example I give you is student ID, course ID. So the enrollment table, it's a bridge table, right? Yeah, it's a bridge table. So Karishma has the best answer. It is a bridge. It's a bridge that is formed based by definition, you see, because all those values exist. So you consider this whole row, this whole table, a bridge table. So fact table is like a bridge table. Because the reason is then I can take any column, they're all primary keys. And then, sorry, they're not primary keys. In a bridge table, well, there are keys that occur multiple times in the bridge. In other words, 91214 occurs many times, just like your student ID can occur many times as many courses as you took. In that sense, it is a bridge, okay? But it can have a separate PK that is not part of any of this. So ignore that part. But the idea is that can occur multiple times. Then I can go and query this. I can say of all the receipts that I have, all the 1 million receipts, tell me all the transactions that happen between 2 and 3 p.m. I can then go and pull that out, right? In that sense, it is a bridge. So let me show you the diagram. Then such a notion, such a way to think about it is called a star schema. It's like a star, a little star, like right there, it's like a little star. So then you are in the middle. The fact table is in the middle of the star. It's a data modeling technique. Maps multi-dimensional decision support data. So it's multi-dimension because each column is now called a dimension. I can have a zip code dimension. I can slice it based on zip code. Show me only 91214. That's a slice on this dimension. By dimension, I mean a spatial dimension, okay? X dimension, Y dimension, Z dimension. Why is there not a W? Could be the fourth dimension. In other words, what is the proof that we live in a three-dimensional world, like our world? Why is it 3D? Why is it not 4D? What simple argument can you make? What simple proof can you give me? What can you tell me? Let me just draw a little picture. Tell me. Why don't we live in a 2D world? Or why don't we live in a 4D? Why aren't we living in a 2D world? Why aren't we living in a 4D world? Anybody? It's 3D. Because what's a simple proof? It's nothing mathematical. It's very simple. What about what I drew? So I can draw any line anywhere. I'm going to call it the x-axis. Just go at an angle. Then I can always say to myself, if you do that, I can always draw a second line that is orthogonal 90 degrees to that. And I'm going to call it the y-axis. And after I do that, I can always draw a third line, which I cannot draw on this, but the third line coming out towards you in the air. That is 90 to y and also 90 to x. That dimension I call the z, the third dimension. And then it stops. We're not able to draw in air or some other way a fourth axis that is 90 to x and y and z, okay? In our world, we cannot draw it. But if somebody lived in a 4D world, then they can do exactly what I'm doing. But then their teacher would actually tell their students, look, I can make a fourth dimension W. In that sense, I can have a fifth dimension, sixth, seventh, eighth, ninth. There's no limit to how many dimensions you can have, okay? Because they're all conceptually 90 degrees mutually to each other. That is what we mean by dimensions. So then you have a cube, but the cube that I showed you was only 3 dimensions. Therefore, I can slice the cube, slice it like that. The slice is now 2D. Then I can slice the cube, the 2D one more time, and it's called dicing. So likewise, I could have had a fourth dimension, which we can show here. And that could be the zip code might be the fourth dimension. Then I can, when I slice on 91210, that means I get a 3D cube that is made up of this, and maybe some other column, but only for 9121 for customers. That's so cool, right? Time machine. Right. So then that is very cool, right? That you can think of all these columns as actual spatial dimensions. This is true for machine learning, by the way, the exact same thing. So then these are called like latent spaces, these are called features and like on and on. So columns are just simply spatial dimensions, 90 degrees to each other. The axis, they're basically coordinate axis, which we cannot visualize, but it's there. Then on that coordinate dimension, on that whole multi-dimension, one sales receipt, like one value for this, one value for this, one value for this, one value for this, would become one point, a single point. Oh, a single point literally in my multi-dimensional space. What the heck? Okay, 1 point. Likewise, some other sales receipt is going to become one more point. They're all just points, okay? We all become points, like every single transaction we make in a multi-dimensional, multi-column world. Okay, now I want to move on. This is a useful idea. Therefore, that's all this is, okay? Therefore, you should be able to put all your columns in this table. And then it creates a near equivalent of a multi-dimensional database schema. So therefore, just by taking your data, like your sales receipt data, and then calling each dimension that you want to analyze a spatial dimension, you can pretend that this whole fact table is a multi-dimensional table, because then you want to slice and dice based on any of these. Like first this one, second this one, third this one, fourth this one, whatever. Therefore, I can just infinitely slice and dice, and I'm getting more and more useful information. I'm zooming in. Hey, cool. All right, so this notion of implement and model, this is where you would do the cube and roll up commands. This command is called cube and roll up. I'll actually show it to you, then we can come back. Okay, the pictures that I'm drawing are here. They are here. So you would run standard SQL, but then now all of a sudden you would say, go to this multidimensional data table that I made, but then do this kind of analysis. So like, look at all this. So you say, select something like all this, right? All this, and then group by roll up. Wow. So this all SQL you've seen before, but now there's one more world, roll up, group by roll up. So roll up means take these two columns and do something special with them. Basically slice and dice based on those columns. And then finally the result that I get, order by the same columns really. So that is this notion of slicing and dicing. There are two called roll up and one is called cube. Slight difference between them, okay? But they're both doing the same thing. So I'll get to that later on. But for now, we're gonna say that this notion of schema, a star schema. Therefore, a star is just a very simple idea that just says, I have this notion of a fact table that is in the middle. Then the dimension tables, which are the columns that all go all around my fact. So the whole thing looks like a star, like this. So even here, say I'm only storing for every sales receipt exactly only 3 things. Where was that sales receipt? What store? When was that purchase made? What exactly was bought? Like maybe 3 different product categories. So somebody went to Southeast and then they bought like on May 12th an HP calculator. Many people bought them. So then if you add all of those May 2012 calculators in Southeast, like in Florida, how much money did we make just by doing that? The answer is 125,000. But then that can be summed up by every single sales receipt through all the millions of receipts where it says location is Southeast, product is HP calculator, and then time is May 12. If you add all those values, which is what Cube and Rollup can do for you, then you will get the number magically. It just pops out, okay? It's pretty neat. And so that is called a star schema where you pretend that the columns are all dimensions, okay? Okay, so then what is in a star schema? The facts are the actual receipts, so we call it the fact table. Dimensions are the columns that you want to do analysis on. Like time matters to me, store ID matters to me. So you call them all dimensions, okay? So then, but the cool thing is this, it is not just only one dimension, you make many dimensions out of them. So in the fact table, you can do more things. In the fact table, even though at the lowest level, my zip code was 91210, right? I also have one more column here that says city. Then in that 91214 is loosely going to say Los Angeles because we're considered part of LA. And then I'll also have a state column that will be automatically filled. The keyword is automatic, okay? Based on this, I'll automatically fill LA and automatically fill California. Suppose there's a US region code, like Western, Middle and then Eastern. This will become the Western cell. You see, this is the beauty, okay? The whole magic is what I just now showed you. That one fact can now inform other columns. So now if somebody says, show me all the things that happened in LA, I would ignore this and go for all the things that look like LA and just pick it up. In other words, I wouldn't have to go through every zip code and say, are you LA, are you LA? That's already done here, okay? So you do some pre-aggregation, and then I can then go up and down. So think of it, it's a cool idea. I just told you that for zip. For time, I can do the exact same thing. One timestamp, like today's timestamp, and it says, March 10th, 2021. But I can make March to be like a quarter. Suppose I have a quarter, first quarter, second quarter, third quarter, fourth quarter. March is first quarter. Likewise, I can have decade. Is it 2020s? Is it 2010s? Is it 2020s decade? So that same timestamp can give me like multiple column of data. Then I can go up and down those columns. So everybody has become almost like a fractal, okay? Yeah, there are derived attributes, absolutely. Yes, correct, they're totally derived. And it's highly useful to store them because then the analyst has all this information at their fingertips, and then you can do this analysis in real time. The opposite is not to store it, but calculate it, but that might take you a long, long time. Say you have like 100 million of these, it won't be in real time at all. So you do the other little trade-off there. So dimensions are what I told you, okay? On the one hand, it is 91214, but on the other hand, it is also, like I said, state, city, region, like all that. And then all those dimensions, everything that you ever search for, they're all called attributes. In other words, the columns basically they're all attributes at any level, okay? It's called attributes. So then the whole thing comes down to slicing and dicing attributes. Used to search, filter, classify facts. But now you can slice on multiple levels of the attribute, right? Like for the 91210 example, I can slice based on 91214. I can slice based on Northern Los Angeles. I can slice based on Los Angeles. Slice based on Southern California. Slice based on California. Slice based on Western US. Slice based on US. Slice based on North America. Oh. And then slice based on the world. So the whole can be at any level you want. And once you slice, dicing is the same as slicing, but you keep going. Like first cut, second cut, third cut, fourth cut, fifth cut. Just cut as many dimensions as you want. You get more and more fine analysis. Cool. Okay, so these attributes that come from these dimensions, right? They're all like in a hierarchy. And again, you can go up and down the hierarchy. Again, 91214, the example that I gave you, Northern LA, California, remember that. It's called the attribute hierarchy. Because even though here it does not look like a hierarchy, there is an implicit hierarchy. Because we know what we do when we create these columns. So then we know we can zoom up and down. Like if you might have a slider literally, this is region slider. That slider can be slid by the analyst in real time, just slide. And then some dashboard would change based on like, are you looking here, are you looking here, or here, or here? The slider can decide to slide it on your phone. It's too cool. Okay, so it's almost time to stop, but I'll do a little bit more, okay? The location hierarchy, again, say you have a location. There's not one location for slicing. They'll ask you at what level do you want the location slice? And you can tell them, I want that at the store level. Just tell me what happened to this store ID 45. The Starbucks, like nobody's going there, why? Or you can tell me what happens to Starbucks like all over Los Angeles, all over California, all over Western US. So it is literally an up and down hierarchy, like a fractal, okay? Like a fractal actually. In other words, once you zoom in, from here, once you zoom in, you would see things. When you zoom in, you would see more things. When you zoom in, you would see even more things. In the store, you can even have per aisle or per point of sale terminal number, or aisle where the product is actually stored. Suppose all the products in Ralph's, they're numbered, right? They tell you the cereal is like aisle number 14. You can even have aisle number as part of this whole hierarchy. And you can even know what happens at a certain aisle. Like, why is nobody going in the back of the store? Well, it smells a lot, but you can find out because, the data will tell you it's evenly populated for all the, aisles, but except the last aisle. Wow. So you can actually learn something about your store. Time, obvious dimension, right? Same thing. You can go from today to like what day of by week. Actually, we just mean what day. Okay, so you can store the day, then you can store the month, store the quarter, year, all coming from today. Okay, the same day. Then you can just open up. Likewise, what can you do to products? Like all products can be just one number, and then product types such as groceries, etc. And then one manufacturer, one product. SQL is 2D table. How are you doing 3D? The 3D is all here. They're all just columns. All these multiple dimensions, right? They're all just columns. So it's all still one 2D. You see what I mean, right? I should probably draw you a little picture. It's all still 2D. That's what I mean. So suppose you think like all of these are all like Southern California. 90210, Beverly Hills, USC, some downtown. I can take all of these and then I can call all of them city of LA, okay? So in that sense, this is a fractal dimension, meaning from this I can zoom into this. But at table level, they all look like a flat two-dimensional table. And then say I have some other, 00 or something, then Rhode Island, I can have, Rhode Island State. So depending on what the zip code is, this is a simple fact. I can have higher levels of aggregation, but all stored as part of one 2D table. So to answer your question, we take all these multiple dimensions, 4th dimension, 5th dimension, 10 dimensions, and fold them. You simply flatten them and fold them to be 2D columns. It's folded column. Yeah, a table is linear in the sense, it is simply rows and columns. But now the columns have a relationship between them. A zip code column, city column, and state column. They're not 3 random columns that have no connection. They are highly connected. In other words, for a state, there will be many cities as part of that state. And then for a city, there will be many store IDs that are all part of that city. So there's some kind of a connection between them. Okay, that's what I want you to appreciate. Otherwise, all this is true. Okay. By flatten, I mean make it go in 2D. By flatten, I mean make them all be like columns, like literally how I drew columns next to each other. I'll draw a better diagram here. Say this one dimension. Say this is the location dimension. Okay. I go by store ID, city, state, region. That fractal is simply called. There's only one 2D table ever. So then they all become separate column names. In other words, that goes here, this goes here, this goes here, this goes here. Say you take a different dimension, time dimension. I want to say, is it morning, is it evening, is it afternoon, is it what day of the week, what month, and all that, right? All those columns will also go here, right here. And then so that maps to here, and then this maps to here, this maps to here. Say there was some other dimension, product category dimension, electronics, clothing, home appliances, personal computers, whatever, right? All those, again, will become column names. They'll all be mapped like right here. So no matter how many dimensions, no matter how many divisions in each dimension, they'll all become one massive flat 2D table. That is one way to do it, by the way. It's one way to do it. But if you do this, then you still need to search through too many rows because it is not as optimized as it could be, meaning all of the city names are all mixed together, right? Because all the zip codes are mixed together. So the next thing we can do is we can then analyze this. And then you can even make mini tables for each city. Suppose a manager always asks, citywide data, right? You can take all the different city occurrences and make separate mini little tables for these. They're all city-based. Then if somebody says, show me Santa Barbara, I can just go and get Santa Barbara for you. So I can have multiple tables that I make from this one fact table over and over and over based on exactly how you zoom in and out, based on what dimension, okay? So you can have further derived tables out of it. Cool. Okay, I'm going to keep going. I'll go a little more than we stop. Okay, so therefore what we just now said was called a star because again, a fact is one fact, but a fact has a relation to all those columns such as zip code, such as time, such as store, product category. So therefore it looks like a many-to-one relationship, meaning one occurrence of 91214. So say this is a dimension, right? So I have a table of zip codes. I just have a table of all the zip codes in Los Angeles, and then what the name of the city is and what the population. So a zip code, a student can take many courses. So 91214 can occur in multiple receipts. Likewise, say I have a state table, and then all the different U.S. states, California, Hawaii, Maine. California can occur in the California column so many times, right? Therefore, that's pointing to many pointers. So it is a one to many, 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 one to many. So the one is all of those actual values in the columns. The many is all of the actual receipts. Make sense? Just one to many. But a star kind of one to many, meaning I can have as many as I want. And I'll put all of the ones on all around. Then I call it this is what makes the star. This is in the middle of the star. Okay. So, and then facts and dimensions related by foreign keys. So once again, all that this means is the fact table has a primary key for 91214. So in this 91214 has some kind of primary key. That primary key might be stored here as a foreign key. Say the primary key for 91214 was like, 4 or something. Then suppose I say 4 here, 4 here, 4 here. Then they all mean like 91214. That way, if these are arbitrarily long, I can have shorter keys for them. That's all. Like one more level of lookup. Okay. Last slide, maybe. I wanted to show you the picture. Yeah, that picture. I'll stop after this and take a little break. All right. So therefore, this notion of a star, I said what I told you. They're all about primary keys and foreign keys. So a primary key of a fact table. It's a composite primary key. This is what I asked you before. It's basically like a bridge table, okay? So it's a bridge table because a bridge is related to many dimensions. In other words, one sales receipt is related to simultaneously the location column, the zip code column, the state column, zip code column, product category column, any number of columns. So you're relating in multiple ways, okay? So like one to many, many to one relationship. In other words, a bridge table. Then it's always a combination of foreign keys, meaning anything that is in here, like say for example 4, is actually something in here. Say I have a state ID 5. It means that there is some row for a state called 5 and probably says main. So this entire thing is a composite that is made up of all these foreign keys. But in reality, what we mean is it is ultimately a huge bridge table. Okay, good. Finally, my diagram, and then we can stop. What I had here, each row, just one row, all those column names are all here in the middle of this diagram. Like it's like an ER diagram. So sales, meaning this is your fact table. I have 3 million sales, 3 million receipts, which is fine. So then for each receipt, we store all these columns. We store the time, the location, customer ID, my club card number, what product was bought, how many of that product did I buy, and then what sales price per each, and multiply by the quantity and the sale and make the total. So it's easy to do it. That's really all it is. So that fact table just stores every single, fact. 3 million facts as a matter of fact. But of the 3 million facts, you look at the time ID, and how many different times can we have anyway? At the lowest level, you can have like all of these. You can have the actual timestamp, hour, second, year, what, right? But afterwards, you can also have a fractal, meaning I can have a year. I can pick out the 2021 from here and then make it part of just the year column. I can pick out the fact that this is March and then make it part of the time quarter column. And I can have quarter 1, not quarter 2, quarter 3, quarter 4. And because it is March in the month column, I can make a cell value be March, right? So what we're saying is all of these are ultimately related to like one fact. Likewise for the product. Once you tell me what the product ID is that you store, I can go in this table and know much, much, much more about the product because the primary key, foreign key, they relate to, okay? The ID is all I have to know to store in the fact table. In other words, I don't want in the fact table to store the fact that I bought a black t-shirt made by Hanes and it is, was manufactured last year and this is the vendor's phone number. All that is useless. Just a product ID would be enough. Then I can go in the so-called dimension table, which is in this case, the product ID, and look up all the information about the product when you just give me that one ID. So because there is a connection between the primary key and the foreign key. In other words, this stores just the least amount of information possible. Then from that one little piece of information, I can then go and infer or store all the other pieces. Like I told you, if I went and bought something right now, it says 7:53 p.m., 3/12, 3/10/2021. I can then take that information and then, drive all of these, right? That's what it is. Is it necessary that the attribute should be directly related to central domain? Yeah, I would think yes, because otherwise there's no point in like having all of those. That the connection, the time, the product ID, like what you store here, yeah, they should be part of some other table somewhere else, sure. Otherwise, there's no need to have those tables. So I think the answer is yes. Okay, what about customer? Okay, they ask you for a club card number or your phone number because that's the primary key really here. Then they can know all about you. They can even send you a coupon. For example, Baskin Robbins might give you a free ice cream because they know your date of birth, because they know your customer ID. And then one last for location ID. All your store is just maybe like a store number or something, like store number 45. But then Ralph's has a table that says store number 45 is some description for a store like corner drugstore. And then where is it in the US, what state, what city, maybe even the manager's name. They can store all of that just based on location ID. So therefore, this becomes a highly useful fact table that then makes a relation to all of these. So the idea again would be one location ID would occur many times in the fact table. One quarter, in March, for example, or January, February, March, so many people bought so many things. So a small number of these can lead to a larger number of these just by repetition. Okay. So in the end, say you have a time like for every single day, right? There's only 365 days really. But obviously there are 3 million transactions that happen in, with a combination of 365 of those days. Likewise, I only sell 3,000 products, but 3 million transactions happen. Where if you look through all those transactions, you find the same 3,000 over and over. And same thing, I have only 125 customers, but amazingly, they bought between all of them. Wow, 3 million things. That's crazy. And then likewise, we only have 25 stores, but we managed to generate so many transactions. Okay, so it's all the same thing I'm saying over and over, one to many, okay. I think we should stop. When we come back, just like next week, I'll tell you what Snowflake is. The same idea as a star, but then that is when I told you, if this becomes too much, this one table, you can start breaking it up into little mini tables, all each at their own level of aggregation. Then you wouldn't need to come back to this main table over and over. When the analyst wants to go up and down, you can then pick the up and down table you already made, except there are separate tables. They're not one big table anymore. So that is more efficient. It's a little bit faster. So we can talk about that, okay? And then I can tell you cube and roll. So we're a tiny bit behind. I'm not worried. It's cool. So when we come back, therefore, what will happen is I'll teach you that, and then that will not be in the exam, okay? So only things that I said up to this minute will be in the exam. So don't worry about the exam part of it, but we'll finish that up. And then we'll start on this brand new idea of spatial databases in NoSQL, okay? Like an introduction to those. So that's it, you guys. Any questions on anything? I'll definitely give you a sample exam for sure. And you can ask all sorts of questions on Piazza. We're happy to answer. Going once? No? Take a little break. So I'm going to come back and then we'll just do some discussions, okay? Otherwise, we'll not talk about this anymore. I'll ask you this when we come back. Except I'm not able to ask you too many things, okay? Well, I'll still try. Okay, so when we come back until 8:20, we'll at least do this, okay? All right, so be back at 8:06. Bye. Yay, we're back. Welcome back. Share. 54 participants. Okay, so let us click on discussion and just ask you a few questions and you get a chance to talk. Okay, I'm gonna put up a chat so we can all see each other's typing. Yeah, ignore these, just go straight. All right, so then we just finished performance tuning, right? So tell me one more time. I love this distinction. So explain to me this distinction one more time. So why do we make this distinction? On what basis? In other words, something else uses a very similar distinction. Sure, very good. So the first answer is perfect. Machine learning versus expert systems. When we say strict rules, probably more technical way to say that would be expert systems. Okay, but you're right though. They're rule based. So then, what are some advantages and drawbacks to those? You think? First, talk about machine learning. So what would be the advantage of collecting statistics and then using it to?
It's very flexible as it's technically self-adaptive.
Okay. What is one more thing you can do with it? Yeah. Generalizations, real time, both of those are correct. Autologous is correct. There's one more that is similar to real time compared to rules. So what do you think that is? There's something about time, the dimension of time, which is different. in both of those. Dynamic rules, changeable. Not those. There's something else that I'm looking for. Like what happens to rules? Let's say you write rules. Then over time, changeable over time. Right, correct. You can do it's changeable over time. Sure. There's one more that leads up to all this. Okay, I'll tell you. It is current, okay? So the nice thing about machine learning data collection is if you do it today, you will get today's data. And that's a good thing because maybe, data access patterns change over time. So always getting the latest is what I was going to look for. Whereas expert systems, it's actually the opposite. Experts are very expensive. And so you interview them, you shadow them, you follow them around, ask them questions. You basically are trying to get what's in their head and then distill them into rules. And then you send them away. It's not they're constantly plugged in and trying to update the rules. So you're stuck with what they have, okay? So that is really the big distinction. And maybe it is enough, okay? But if you want something more up to date, data access changed, you have to actually go to machine learning. Hey, cool. Tell which timestamp is important. Yeah, all that is true, definitely, you always keep the latest, you can throw the old ones away. Okay, hashing. So I mentioned that what the SQL cache is about is actually to take your SQL queries and then run a hashing algorithm, get a hash key, and then use it to sort and store compiled action plans so you can quickly look them up. So in the real world, online especially, we use a certain thing quite a lot, some of us, others not much, where hashing is just commonly, openly available. It's obvious that they're hashing. Passwords, I don't mean necessarily, encrypting for that reason. It's more like a pointer. Barcode, you're getting colder, definitely not about barcode. Okay, so online, with websites, web services, hashing is employed. Public key, you're getting colder. So again, this is not hashing for cryptography.
I'm not thinking about dictionary because I don't know if that counts. Like, basically, dictionary is sort of like a hash map style data structure.
Sure. But the dictionary is used for what though? Like you and I don't openly go and use a dictionary on the web, right? So there's something that we do where we use it without even knowing that we use it. Let me see if I can. It's like a service that some sites offer. That's a hint. It's a big hint. That service, not cookies. There's something that simplifies your life. They're using it to make things simple for you. Not DNS, although that's a cool answer. But DNS is not about hashing though, Exactly, wonderful. Karishma got it. All the URL shorteners, right? That's exactly what they do. So if you go to Bitly, right? I use Bitly a lot, okay? So if you go to Bitly, then anything that, I've entered in Bitly, for example, CS Robotics Survey, somebody else put this up. That is like a hash key, okay? So that hash key will always take them exactly to this real URL. This is the one that the researcher wanted the whole world to use, but no one is going to remember there's a bookmark. They'll think it's a waste. So then you can tell somebody, just go to CS Robotics Survey, okay? So therefore, the Bitly site, I made one. This is actually amazing if you want to look at it. It's about disinformation. I want to start talking about it now. Scary, crazy, weird, cool, all at the same time, okay? It's about like where fake news came from. Okay, so I gave this talk, but I didn't want all the students to go and type this in even for the first time. I told all of them, just go to Bitly, and then do, AMS 2019 DIS for disinformation. So that is a URL shortener example, okay? Where in Bitly, this is all they do. You give them a real URL, and then they'll give you a shortened version. Like right there, shorten. Just click one. Let's actually try it, okay? What if you could do this? They're generating a hash key for that particular URL. Let's go here, and then shorten that. So that is the hash key, because only this link could have generated that. So then what happens is forever, they store this as a key. And then they want, you to give this to people. Then when somebody clicks on it, they'll look up a key value and then do a DNS redirect. They do a forwarding so that it actually goes to the real site. You can try it, okay? So that's an example of hashing that is used. It's actually very cool. By the way, I don't know if you know, once you create one of these, you cannot ever delete it. So they'll never reuse this at all. So the forever that's going to be associated with this page. Even if I take this page down, the link would be broken, but they'll never reuse the link. You cannot give it back. Yeah, it is pretty cool. So it's like you're showing. Okay, cool. So Karishma answered it. Yay. So then the opposite of that, meaning, so what if you're trying to hash something, right? So I send many URLs, right, to my hash function, but then they all give me the same key. Then it's called a key collision, right? Then that's called a hash collision, because too many different strings are generating me this exact same hash key. So what is the worst case if that happens? Like, how can you deal with it? There should be, yeah, I know there should be, but they never delete it. Just never. There's not even a way to ask for it. Yeah, linked list of what actually? Rehash. You can rehash, correct?
So basically, I think the way is that for every hash entry, which is more like I'm resorting to hash map. So basically, for every hash map entry,
Mhm.
the key is the hash, and the value is actually a linked list of objects that has the given hash.
Good. All the objects that hash to the same key. Yeah. So in this case, though, they have a problem because if I get this key and then I think that people are going to go to my site, and then if you use your URL and you're also given the same key, unfortunately, in the Bitly case, they can only redirect to one. So maybe the last one would win, okay? But in general, though, what you're saying is correct. What will happen is when you have multiple indexed, keys in the hash same bucket, meaning many different URLs are giving me the same key, then it's not the end of the world. I can actually put them all in the same bucket, meaning I can hold on to all those objects and find some other way to distinguish, what the actual object should be. Or at the worst case, in a database situation, I can just send the user like all of those objects and say, I got all of these. So the collision is not like the end of the world. What about the unbalanced B trees? And I asked earlier, so what would happen, like what is this equivalent to? In the limit, what happens when you have a B tree, some kind of binary tree in general, okay? What happens if the tree is heavily imbalanced? I'm gonna ask you. So suppose there was a tree like this. The tree actually went like that. Like that. Like that. So from here, it's extremely unbalanced. So what is the problem with looking things up? So see, these are all leaf nodes here, right? These are all leaf nodes. So I come here, and then I do a binary search, and I'm constantly I'm trying to find this one. Then I have this. So I first decide go this way. Then I come here, then I decide go this way. Then I come here, then go this way. This one is maybe null. I find it. So finding is not the problem. But then what happens, like what is the practical implication of something that is heavily imbalanced? What happens to your search time, basically? Exactly. Very good. It becomes a linear list, right? So it goes to O(n) is the point. I mean, in the ultimately worst case, suppose there's no left branches at all, okay? Suppose it is so imbalanced that, this is the only way to look something up. It's like so weird, right? Or as imbalanced as possible. Yeah. So every one of them leads to exactly like one, left leaf. Then that's basically O(n) search. In other words, say you want to find this. My binary is not helping me at all because I need to go through every single one of them and say not this, not this, not this, not this. Wow, on that. So that is an O(n) search. So you go from O log n to actually O(n). It makes it highly useless. So the different way of saying that is these kinds of data structures always strive to keep their trees balanced as well. But I wanted to see if somebody would tell me that. In the limit, a highly unbalanced tree is as good or as bad as linear search, then might as well not make the tree. Okay, what about this one? So what are some practical columns in the real world, like in your examples, in your life or in your things that you do business with, where there are columns that are worth creating indices for? Indices are useful. I named one of them, for example. In Facebook, if they have a column, like a field for birthdays, they'll definitely index the birthdays. Then every single day, they don't have to go searching through 2 billion people. They know whose birthday is coming up. So give me some other examples like that. You can think of Amazon, you can think of Grubhub, you can really think of anything you want. Quantity on hand. Yeah. So what would be the reason you can definitely do it. It's a nice integer, right? So what would you use it for? I guess you would say, give me all the products for which I have 4 pieces of, like 4 quantity on hand. I guess you can do it. Car brand. So what do you mean by car brand? Amazon sellers. Garima, I lost you on the one.
So there's like maybe 2 billion cars, or okay, like everyone owns one car, and then you don't want to go through, like, if you want to just get how many Toyotas are in the market, then you don't want to go through like 5 million cars just to check what brand it is.
Interesting. That's actually cool, huh? This could be very true actually, like Kelly Blue Book or something, right? So Kelly Blue Book, for people that don't know, they give you like a price, like a reasonable price for used cars. So if you want to sell your car, the first place that you go to is Kelly Blue Book, and then you type in the condition of your car and all that, right? What? Then they'll tell you what is my car worth. I mean, that's the whole point. See in there, I think Mansoor is quite right. So maybe if you want to start by saying what is my car worth, the first thing they're going to ask you is what make, what model of your car, and maybe the index based on that. Even though it might not be a primary key, right? Because primary key might actually be something very different. But yeah, you can index based on those columns. Events happening. So what do you mean? In what context are you talking about events happening? Amazon sellers, Garima, can you tell me a little bit more? Item name. Yeah, definitely item name. You can index that because a lot of people search for just items like cookies and hammers and things. Yeah, okay, I've run out of time. Maybe Yash can quickly tell me events happening. What do you mean by that, Yash? Maybe you can search by event name like birthdays and things, or maybe you can do that. Probably meetup.com can actually, exactly. Very nice. Yeah, cool. Jinx. Okay, I think on that note we should stop, because it reminded me all the time. Cool. So see you at the midterm. Okay, is that true? Actually, no, not see you at the midterm. We still have like next week. I'm sorry, I apologize. But until what we said today is what is going to be like on the midterm, right? Cool. Okay, so everybody take care. See you next week. Bye.